Alright, sound check. Do I hear myself? It looks like I can hear a click. Yep, I hear myself. Next is audio, or rather video check. So let's switch that off and do that and see if I can see my hand over there. Yes, I do. Okay, perfect. Sorry for having to postpone this multiple times, but it's been quite the week. I had a headache the day that I was originally planning to stream this, which was what? Monday? If I'm remembering correctly. So I didn't feel comfortable streaming that day. I took care of other chores instead. And all this week, people around me have been getting sick, and I've been needing to cover for them. So, yeah, that was fun. But I'm back, and we are still moving at a pretty good pace. I think we'll be finishing probably in the middle of March, if not by the end of March. We should have pretty much all of April as review time, and I think once we get to that point, I'm going to maybe take a break for a week or two, or, actually I'm not entirely sure what to do about that yet. We'll see, I'll have to think about it more, but for now, let's not dilly-dally. Let's get to what we need to cover for today. So today, I want to talk about the topic of torque. Today, I want to talk about the topic of torque. And after thinking about it, I also plan to, at the end, talk a little bit about moment of inertia and center of mass. I mean, we're going to talk about center of mass a little bit when discussing torque because we're going to need it for some of our problems, but I'm going to look at it a little more deeply at the end, and that ending part will be for the Physics C students specifically. Physics 1 students, I'm going to do it all algebra-based, so you're more than welcome to stay and watch. Maybe it'll be beneficial to you in some way to know the math behind it, at least the algebra-based math. But it's not officially something that you are required to know. That being said, I have seen questions on the AP exam that ask about, there was this one Physics 1 question that was, it was a graphing question, and it was about a collision, I think, and it was asking about, like, what's the velocity of the center of mass of the system of objects. So, I don't know. The course description says that you're not required to learn how to calculate center of mass, but that problem would suggest that you would need to know. So I don't know what's up with that, but it's easy enough. So if you want to stick around for that ending part, you're more than welcome to do so, but according to the course description, it's not required of you. It's only required of the Physics C students to do it, both algebra-based and eventually, when I come back around to it, calculus-based as well. So those are our topics. Torque, static equilibrium, that's going to be the majority of today. At least that's what I'm expecting it to be. We'll see how much time we actually end up spending on it. And after that, we'll touch on center of mass, calculation, and moment of inertia. Well, moment of inertia first and then center of mass. So, torque, what is it? Basically, it is the rotational effect of a force on an object. That's one way you could describe it. It's the rotational effect. The rotational effect with an E is a noun. Effect starting with an A is a verb. The rotational effect of a force on an object. That's basically what torque is. And I showed the formula for torque, I believe, way back in the first episode, Unit 0, when we were talking about the different kinds of vector multiplication, the different kinds of multiplication you can do with vectors. Torque is a cross product. Torque is a vector, and it is the cross product of this variable r and force. And this variable r, I guess you could call it lever arm, but lever arm has a more specific definition that renders this cross in the cross product kind of redundant. We'll talk about that when we get to it. But yeah, a cross product, it's when you take two vectors, multiply them by each other, you get a third vector, and a cross product is always perpendicular to both of the original vectors. So if I were to take my pens over here and hook a couple of them together, let's say like this. So let's say this red pen is R and this navy blue pen, which probably looks black on most of your screens, is going to be the force vector. So the order matters. R cross F is not the same as F cross R. The order matters. So you don't need this for AP Physics 1 or AP Physics C Mechanics. The electricity and magnetism students, you do need to know this. There's something called the right-hand rule that determines the direction of a cross product. Right-hand rule. There's actually 3 right-hand rules for those of you taking electricity and magnetism, but you'll learn about those when you get to them. Actually, by this point in the school year, unless you were taking electromagnetism strictly in the second semester, you would have already encountered it, because it's something you come across really early. Like in the middle of the first semester, if you're doing it as a 2-semester course, and I guess somewhere around the end of the first quarter if you're stuffing it all into a single semester. So right-hand rule, or RHR, as it's sometimes abbreviated. There's actually 3 of them. We're just going to worry about one of them today, which I like to call the palm right-hand rule. Palm, P-A-L-M, because it depends on the palm of your hand. So here's how it works. Basically, you take your fingertips and you make them point in the direction of the first vector in the cross product, in our case the R. So I said that was the red pen. So I would take my fingertips so that they're pointing in the direction of the pen. Hold on, let me move the red pen a little bit so that this is more comfortable on my hands. Okay, there we go. So fingertips need to be pointing in the same direction as my first vector. And notice that there's more than one way I can orient my hand while still having my fingertips pointing in the right direction. So now comes in the second part, the second vector. Your palm needs to face either the direction of the second vector directly, if it's completely perpendicular to the first vector. It's not, it's a little bit off from 90 degrees. But then if you were to break it into components, it has a component perpendicular. This navy blue pen has a component perpendicular to the red pen, which I've represented with my green pen over here, and your palm should be facing that direction. Another way to think about it is you want to keep on rotating the direction of your hand along your wrist until you are in such a position that when you try to close your fingers, you end up touching the second vector. And if you do that correctly, then your thumb should be sticking out, pointing in the direction of your resulting vector, pointing in the direction of, in our case, the torque. So if lever arm is this way and force is this way, then the torque has to be this way. In fact, I can rotate the direction of the force like this, and the direction of the torque would still be this way. As long as the component of the second vector that's perpendicular to the first vector is still in the same direction, then yeah, the torque is still going to be pointing out of the page. Now, what if I were to do the opposite? What if I were to do F cross R? What if I were to do F cross R? Well, in that case, fingertips are now in the direction of the force vector because that's the first vector in the multiplication now. And if I try to rotate around my wrist, I have to open my palm in this direction so that my fingers can curl towards my second vector. And now my thumb is pointing into the page. So now I'm getting the exact opposite direction. R cross F is out of the page. F cross R is into the page. And what that direction means as far as torque is concerned is not really all that useful to us. It's much easier for us to just think about torque as having a clockwise or counterclockwise direction. But yeah, we can use the right hand rule to assign a direction to it. In this case, in my two examples, either out of the page or into the page, in the positive z direction or the negative z direction. And if it helps make it a little bit more intuitive, it's kind of how screws work. Let me grab this screw that I happen to have lying around, as one does. So if you were to drive a screw, so if I were to, let's see, if I were to apply a force on this screw, I would be applying it, I guess, let's say in this direction, causing it to go clockwise, and clockwise would be into the page. That would be, I guess, how do I want to do this? Well, it'll make more sense once we actually see an example. Hold on. I'll get back to the screw in a minute. So let's say I have a stick. And let's say I have it nailed down at one point over here. We call this point the hinge or the pivot. I prefer the term pivot because a hinge implies that it's an actual hinge like a door hinge, when sometimes objects can be pivoted without the use of hinges. But yeah, if I hold it down here and I apply a force on it over here, for example, then that force is being applied at a distance of r away from the pivot, like so. And if I were to do my right hand rule, fingertips in the direction of r, my palm is in such direction that my fingers can curl towards the direction of force, I guess I would draw the force. Where would I draw the force? I guess I would draw it over here. I would connect them tail to tail. And then my fingers would curl towards that, and my thumb would be pointing outward. So this, if I were to push an object like this, it would cause a counterclockwise rotation. So let's grab this ruler. Whoa, almost knocked everything down there. That would have been bad. So let me grab this ruler and let me hold it down over here and let me apply a force on it this way, and that causes it to rotate counterclockwise. So we are going to say that counterclockwise is positive because when I did my right hand rule, I got my thumb pointing up. that means that clockwise would be negative. So let's think about the way that our screws work. So with a screw, you drive it by rotating it clockwise. You rotate it clockwise, and which direction does it go? It goes down. Now, this is because of the way that we design our screws. It has nothing to do with the right-hand rule, but it might help you just remember that clockwise torques are downward torques, torques in the negative z direction if you're just looking, at a flat surface and using your traditional x and y coordinate system on that surface. But it doesn't actually have any physical meaning outside of that. The torque being into or out of the page, that's just something that we use for, I guess you could say, mathematical convenience. That's just something that we use for mathematical convenience so that we can assign torque a positive or a negative value in case we ever need to add one or more torques. We would have some sort of direction to associate with it. But otherwise, what's more valuable to us isn't the into the page versus out of the page direction of torque that we get from the right-hand rule. It's just what we can see with the naked eye without the need for the right-hand rule in the first place. Is it clockwise or counterclockwise? And by default, counterclockwise is what you should have been taught is the positive direction in your math class if you learned about the unit circle and all that in your pre-calculus class. If you haven't taken pre-calculus and you're an algebra student, maybe you're a middle schooler who's taking physics really, really early, you will learn that stuff. But for our purposes, we're just going to decide on the fly whether we want clockwise to be positive or negative based on the problems that we're given, because it's not really going to matter. We'll just choose a direction and declare it to be the positive direction, and then everything opposite of that will be negative, and that's just how we will go. Kind of like what we've done before in previous chapters. For example, what we've done with some pulley problems where for each object in a system of objects connected by ropes over pulleys, we would just decide, maybe for the block that's hanging off the side of the table, we decide down is the positive direction instead of it being its usual negative value. That wasn't even a good sentence. Its usual negative value. I can't put words together today, but you know what I'm trying to say. Traditionally, we think of down as being negative, but there have been cases where we've used down as positive for the sake of convenience, and something similar is going to happen today. Something similar will be done for some of the problems that we'll be seeing today. So let me see. We define torque, both in words and mathematically. We haven't yet analyzed all these factors that go into it. Okay, so basically if I were to, let's draw this stick again. Let me draw that again. And this time I'm going to draw it with the force acting in this direction. Okay, so this R thing is supposed to be the distance between the pivot. It's supposed to be the perpendicular distance between the pivot and what's called the line of action of the force. So if you take the direction of the force and you just continue drawing a dotted line in either direction, it doesn't matter whether it's forward or backward, and you draw a perpendicular line from the pivot to that dotted line, that is supposed to be your R. That is supposed to be what's called your lever arm. So this is called lever arm. Lever arm, or sometimes called moment arm, or sometimes it's also called moment arm, because torque can sometimes be called the moment of force. If you ever see the term moment of a force, then that's just another way of saying torque. But most problems you'll see will just refer to the word torque. They'll just refer to torque by the word torque. You might see it maybe if you're looking in, I don't know, some unassigned physics textbook, or maybe if you're reading some sort of research paper that has something to do with this topic, you might come across that, but I wouldn't worry about seeing it on the AP exam. But just in case you do, now you know. So that's the definition that they go with. I don't like this definition because we're going to see situations where we're going to have multiple forces acting on an object and creating torques on that object. And once you draw all of these action lines, all of these lines of action for these forces, and you start drawing lever arms to them, the picture is going to get really, really crowded, and it's not going to be pleasant to look at. So I have a different definition for this R thing. I like to call it the displacement from the pivot to the point of application of the force on the object. So I like to define R this way. So I'll try and redraw this. I'll try and redraw that. So we'll say that we're pivoting over here again. And we'll say that I have a force being applied in this direction. And as far as I'm concerned, the point where the force is being applied, that is where I'm going to draw my R to. My R is going to be the displacement from the pivot to the point that the force has been applied. If you look up videos other than mine, they will probably use this approach where they just draw a perpendicular line touching the line of action of whatever forces they're looking at. I don't like that. This is my way, but if you prefer this other way of doing it, fine, suit yourself. Both methods are going to be equivalent, and I will show that momentarily. But this is how I'm going to define things. I'm going to look for the point on the object where the force is being applied and take the displacement from the pivot to that point, and that's going to be my R. And of course, if there's multiple forces, then there's going to be multiple R's for each of those forces. So what I really should have done over here is I should have called this R1, and this is F1. And then this over here in pink is F2, and this would be R2. Each force will have its own R associated with it. Don't assume that forces have the same R's associated with them. So why do these factors matter? Well, you probably have swung many doors in your lifetime, and you've probably noticed that it's easier to swing a door as far away from the hinges as possible. I'll just demonstrate with this ruler. If I hold it down over here, the greater the distance from the place that it's being held down, the less force I have to apply to make it rotate really easily. And the reason I can't rotate it very far is because I have other stuff that you don't see over here on my desk that's getting in the way. But you know from experience that I'm not trying to pull the wool over your eyes. You know that You don't have to apply as much force if you're applying it very far away from wherever an object is pivoted, wherever an object is held down. So the greater the magnitude of R, the greater the torque. So far that's checking out with our math. The second factor is, of course, the force. It makes sense that the more force you put in, the faster it'll rotate, the more rotational acceleration it'll gain. And we will talk about the rotational acceleration part of it in the later part of this stream when we bring up moment of inertia, because we kind of need that in order to understand it properly. So that'll be much later. And the third factor is the angle. If I apply a force completely perpendicular to the object, completely perpendicular to R specifically, not necessarily to the object itself, because the object could have a weird shape. But if I apply a force perpendicular, then that is where I would get the most amount of rotation for my force. If I apply my force at an angle, then, well, it rotates less. If you try to push or pull on a door at an angle instead of just directly at 90 degrees or nearly 90 degrees as we're used to doing, then you won't get it to swing as easily. And if you apply the force along the direction of R, whether it's pushing or pulling, if I apply a force this way or this way, if you try that on a door, what happens? Well, if you're not strong enough, then nothing happens. The door just doesn't budge. But if you are strong enough, then you're probably going to break the hinges, and your parents are going to be mad at you, and they'll probably make you take a summer job to pay for the repairs. So let's not do that. And if you do end up doing that anyway, don't you dare blame me for it. But Al, the tutor told me to. No, I didn't. No, I didn't. This is my disclaimer. This is, if your parents end up suing me for a door that you broke, I am taking the clip from this. I'm taking this clip, and that's going to be my entire defense. I once had a student do a different demonstration. I'll bring it up later when we discuss angular momentum, which is not today. He did this angular momentum experiment that allows you to speed up your rotation when you're already rotating in a swivel chair, and he somehow ended up kicking a hole into his bedroom wall, I think. Something like that. I just remember something broke, either the wall itself or something at the bottom of the wall. I don't remember the exact details, but yeah. Anyway, the third factor is the angle, and some of you might be saying, well, wait a minute, where's the angle in all of this? Well, it kind of showed up over here, where the official definition of lever arm requires the lever arm to be perpendicular to the line of action of the force. If you think about it, compared to what I do for lever arm, what this is doing is basically, it's taking this distance, what I would call R, the thing that is R under my definition, this over here, and it's taking a component of it. And that component is going to be the sine component, where the angle is going to be this over here. This is going to be the angle. It's probably not going to be very visible because, like I said before, the problem with this trying to draw things perpendicular to the line of action is that your drawing gets really crowded. I mean, drawings for force diagrams for torque problems are often going to get crowded anyway, but I think having to draw lines of action for forces just makes the crowding even worse. So I don't like it. But yeah, that's the angle. So if you were to take the force vector and this r vector, at least the r vector as I define it, you know what? I need to come up with a name for it instead of just calling it r as I define it. Let's call it pivotal displacement. That is a name that I just made up on the spot. Pivotal displacement. Pivotal displacement. Patent pending. I don't think I can patent this, but pivotal displacement. Oh, and of course, trademark. Wait, no, you don't put the trademark on the... There. Pivotal displacement. Trademarked and patent pending. Pivotal displacement. Al's version of R in the torque equation. So if we... I lost my train of thought. What was I even going to say before this? Right, so if we draw the pivotal displacement vector and the force vector tail to tail, I guess you could also draw them tip to tip if you wanted, then the angle that they make with each other when drawn that way, that is the angle that is being used here. So if I were to take these two, for example, if I look at this last one that I drew and draw R like this, and F was like this, then this would be my theta. Actually, you could even use this as your theta, and that would be fine too. I'll call this one phi. You could use either of these angles, and you'll end up getting the same result. Because what you're going to do is you're going to multiply the magnitude, so the magnitude of your torque equals the magnitude of your pivotal displacement times the magnitude of your force times the sine of theta, which is going to be equal to the sine of phi. If you did pre-calculus, you already know that sine of theta is equal to sine of 180 minus theta. If you learned your unit circle, 180 degrees minus theta. If we're working in radians, that's going to be pi. Oh, and by the way, let's actually talk about this. So, for AP Physics, there's going to be in the simple harmonic motion chapter one situation where you might want your calculator to be in radian mode. So if you find the mode button, I don't know what kind of calculator you have, but if you find the mode button and pick radians over here, then that will take your angles in radians whenever you use trig functions. But for the most part, you are going to be working in degrees. I think I warned about this way back in one of the earlier episodes as well, but if you're taking pre-calculus or calculus or trig at the same time that you're taking your physics course, then you have to get in the habit of constantly checking what mode your calculator is in, because you end up doing radians in your math class, you come to your physics class forgetting to switch to degrees and you get all the wrong numbers, or vice versa. You come from your physics class to your math class, your calculator is still in degree mode from physics, and you end up getting the wrong things because you're not in radians in your math class. So be on the lookout for that, check for it. But yeah, let's say that we're in degree mode, because that's what we often use in physics. Sine of 180 degrees minus theta is equal to sine of theta. I can prove it to you right now. Well, not prove it per se, but if I do sine of 60 degrees, I get root 3 over 2, and if I do sine of 120, which is 180 minus 60, so sine of 120, that is also square root of 3 over 2. You can do this with any pair of angles. You can do sine of, let's say, 20, and I get 0.34 something, and sine of 160, also 0.342 something. So if you haven't learned it in pre-calculus yet because you haven't had pre-calculus, or you had it and you just completely forgot that part of the course, now you know sine of theta is equal to sine of 180 minus theta. So conveniently for us, it doesn't matter which of the two possible angles you choose when drawing your pivotal displacement and force vectors tail to tail or tip to tip. Whichever of the two angles that you can get between them, just plug it in and you will get the correct result for the magnitude of your torque. And of course, the highest that it will go is sine of 90 degrees, which is 1. And yes, those of you who haven't taken pre-calculus, you can take sines and cosines of angles that are greater than or equal to 90 degrees, even though there is no right triangle with two right angles. There's a reason for that. The definition of sine and cosine, it's not something we're going to go over in this course, but open up your pre-calculus book if you have one and go read up on that, or just go to Khan Academy and look up their lessons on the unit circle definitions of sine, cosine, tangent, and all that. So that's what you want to look up if you are a student who has not had pre-calculus and trigonometry yet. Just food for thought. You don't actually need to know it for this course, but it can help. It gives a little bit of extra context. It gives you some comfort with what we're doing at the very least. So let's see. Where was I? Right, so sine of theta. Its maximum value is when theta is 90 degrees. Right, we know that from experience. A situation like this, where the force and pivotal displacement are at a perfect 90 degrees to each other, that is when you get the most bang for your buck. That is when you get the most rotation for the amount of force that you're putting in. That is when you have to put in the least effort to get the greatest results. So those are the three factors. Distance from the pivot, or lever arm if you prefer this definition instead. Magnitude of the force, that's self-explanatory, and the angle. If you optimize all three of those, you can get a lot of torque. Whether that's a good thing or a bad thing, I suppose it depends on the situation. Sometimes you don't want things to rotate. Sometimes you want things to stay balanced. Or you want them to rotate but not too much, like, say, a Ferris wheel. You don't want it to rotate too fast. Otherwise, that could be dangerous. Let me think here. So, we've gone over basic torque now. We did touch on torque by multiple forces. Oh, right, and also over here. So, since this definition of R takes this distance from the pivot times the sine of this angle to calculate your R1, which then gets multiplied by F1, it still ends up being R times F times sine of theta. It's just that you use the sine of theta to take the component of this distance over here, or rather this displacement, the pivotal displacement, instead of using sine theta to take the component of the force. Because that's another way you can look at it. Come to think of it, I forgot to mention this. Another way you can look at it is that these angles can be used to just get the component of the force that's perpendicular to this R, if you use the definition that I'm using for R. If you take the component of force that is perpendicular to the pivotal displacement, if I take F sine of phi over here, then I think you can see, if I were to draw it over here, this would be F sine of phi, which we already said is equal to F sine of theta, because 180 minus theta will give you the same sign as theta. So yeah, that's another way you can look at it. You can look at it as take the component of the force that's perpendicular to the r, or take the component of the r that's perpendicular to your force direction, or just treat r and f as being whole vectors without worrying about their components, and just think of it as multiplying by the sine of the angle between their directions, and just don't associate this angle with either one of these two vectors, but rather with the, I guess, combination of both of them. So 3 different ways you can look at it. Whatever feels most intuitive to you, just go with that. If you like to think of it as taking this official definition of lever arm, fine. You calculate this distance, you multiply by the sine of the angle, and you get this perpendicular distance. If you want to think about it this way, take the component of the force that's perpendicular instead, and don't touch the distance between the pivot and the point that the force is applied to. That works too. And if you just do what I do, draw your pivotal displacement, draw your force, and then just, you don't even have to redraw them necessarily. You can just kind of picture it in your mind what they would look like if you drew them tail to tail or tip to tip, and figure out what that angle is and just multiply by the sine of that angle. That's the approach that I will be using. So multiple forces acting on the same object will create multiple torques. Some of those torques will be clockwise, some of them will be counterclockwise. If you have opposite torques, then obviously they will add, or not add, well, they will add, but the ones that are in the opposite direction will be subtracted from the ones that are in whatever you consider to be your positive direction. So multiple forces acting on the same object, generating multiple torques. Those torques combine. If they're in the same direction, they just add up to a greater magnitude. If they're in opposite directions, you get a lower magnitude. And then whatever is left, that is called our net torque. Net torque. So net torque is simply R1 F1 sine theta 1. Well, actually, hold on. The way I've written it, rather, I want to do magnitude of net torque. Will be, I don't need these vector arrowheads, just the magnitudes. R1 F1 sine theta 1 plus R2 F2 sine theta 2 plus R3 F3 sine theta 3, and so on and so forth for however many forces you have. But make sure to remember to also add a negative sign for some of these depending on the direction of the rotation, clockwise versus counterclockwise. You will decide what you define as the positive direction for each and every problem. And once you've made that decision, everything opposite to the direction you've deemed as positive, just remember to put a negative sign in front of it, because this equation doesn't really have anything built in that reminds you to do that. So you're going to have to remember that part yourself. All right. Next thing I want to talk about then is situations where the net torque is 0. And this is where we're going to linger for a bit. Now I want to talk about equilibrium. Uh-oh. There we go, now it's working. Okay, equilibrium revisited. Static equilibrium, to be specific. Equilibrium revisited. So, we once upon a time said that the conditions for an object to be in static equilibrium is that the net force on it needs to be zero. That is in all directions. Net force in the x direction needs to be zero, net force in the y direction needs to be zero, and if we were doing three-dimensional problems, net force in the z direction would have to be zero. Well, that wasn't the entire truth, and I think I hinted at it way back then that there was one other factor that we were ignoring, which is where the forces are being applied on the object. Because now that we know about torque, it matters where you apply these forces, right? You're going to get different torques depending on whether the force is applied here, or here, or here, or here, or wherever. So it's very important now to take that into account. In order for an object to be in static equilibrium, there is another condition, which is that the net torque on the object needs to be zero, and it needs to be zero for any pivot, for any and all pivots. Let me see, is that visible on the screen? Yes, it is. Okay. I need to double check whenever I write things towards the very top or very bottom of the page, because I've noticed sometimes that gets obscured because I shift the paper around a little bit and it gets out of the camera view. For any and all pivots. Okay, so this sounds like we have to prove that the net torque is zero for an infinite number of possible points. So, first of all, let's talk about all the different pivots you could have. So if I have this ruler, of course I tried pivoting it over here on its left end earlier, and yeah, you'll get some results from that if I push it, this way. I get it to rotate counterclockwise. If I push it down, rotates clockwise. But I can pivot this thing at other places. I can hold it down over here, for example, and I can apply the force at the same point, which was somewhere in the middle over here. And now applying a force up causes a clockwise rotation, whereas applying a force down causes a counterclockwise rotation, the opposite of when the pivot was on this side. So a change of pivot without changing the forces acting on the object can change the magnitude and direction of the torque due to the forces acting on the object. If I still have two forces acting on an object, if I were to exert two forces on this ruler like this, let's say that they were equal and opposite. I don't think I can precisely get my fingers to exert an equal amount of force, but let's say that they were equal. Let's say that I got nearly equal forces over here. Well, holding it like this, I guess I would be creating a pivot around here, and that would mean that this force is creating a counterclockwise torque, and this other finger that's pushing downward is also creating a counterclockwise torque. So even though the forces cancel out, even if the forces were to cancel out, the torques don't. The torques add. So this object would rotate. And that's not equilibrium. That is not equilibrium. So we need the net torque to be zero, and we need the net torque to be zero for any and all possible pivots. If I had, for example, an object that's held down over here, let me actually put this to hold it down. Just 250 grams of little slotted weights. Let's say I hold it down over here, and I apply a force on the ruler. I apply two forces over here, like right where it's pivoted. And what you don't see is that the forces are unequal. Maybe the force of my finger pushing down is greater than the force of my other finger pushing up. And that's not visible because you've placed the pivot here, and when you apply a force at the pivot, well then R is 0, and the torque due to either force, regardless of which one is stronger, is going to be 0, so you see no rotation. But then if I move the pivot and I still have the same forces, and again this force from above is stronger than the one from below, well now there is a net torque. So it's not enough to just have one pivot where the net torque is 0. For an object to truly be stable, for an object to truly be in equilibrium, the net torque needs to be 0 around any and all pivots, which sounds like a very difficult task to prove. But fortunately for us, very similar to uniform circular motion, we usually work from the effect side of the problem. Usually we will be presented with problems, well, by usually I mean always, because I don't think I've ever been presented with the alternative scenario. So yeah, I'm going to say always. Watch me put my foot in my mouth when I come across a problem where that's not the case. Because that's always going to happen when I least expect it, at the worst possible time, right? Anyway, so we're going to get problems where we are told that something already is stable. We will get problems where we're told that something is already stable, which means that this for any and all pivots stipulation actually works to our benefit. Because if an object is stable, if an object is in equilibrium, then what this means is we can work backwards from the conclusion. We see the effect is that the net torque is 0, therefore we can conclude that the cause... Hold on, I worded that wrong. We can see that the effect is that the object is in equilibrium, so we can work backwards and conclude that the cause was the net torque being 0 for any and all pivots. That means we can pick whatever pivot we like. That means we can pick whatever pivot point we like. And that is going to come in very handy once we do equilibrium problems, which I think we should go ahead and do, because that is probably the best way to make sense of all of this. So, when drawing the diagrams for the problems we're about to do, it is important to know where the center of mass / center of gravity is for an object, because objects on Earth are going to have a gravitational force acting on them, and now that the position where the force is being applied matters, we need to make sure to draw the force of gravity in its correct place. The force of gravity acts on an object's center of gravity, which is basically the same as its center of mass as long as you're working in an environment where the acceleration due to gravity is approximately constant. We did the gravitation chapter recently, so you already know you can go tens of thousands of meters before seeing any appreciable change in acceleration due to gravity. So if we're just doing basic human scale experiments, center of mass and center of gravity will basically be in the same place. But if you want to know the difference, again, I will talk about that towards the end today. But for our purposes, especially for the Physics 1 students, just draw the force of gravity on the geometric center of the object. If the object is a stick, draw the force of gravity on that stick halfway along the length of that stick. If it's some sort of square piece of board, draw it right in the middle where the diagonals of that board crisscross each other, and so on and so forth. If the object is a circle, draw the force of gravity at the center of that circle. That is for the Physics 1 students. For the Physics C students, we'll talk about how to deal with the center of mass, center of gravity being in other places later. So where do I want to start? Which of these would be good to start us off? Well, I suppose we can do one that doesn't have equilibrium first, just as a sort of warm-up, and then we'll look at one with equilibrium. Is the backside of this available? Yes, it is. Perfect. Okay, so this one is a really, really bare-bones example. It doesn't even have any sort of story or context behind it. It's just some random object that they drew with 3 forces on it. So they drew this object, and it says calculate the net torque, magnitude, and direction on the beam in the figure about an axis through, let's see, an axis through this point, through the end, perpendicular to the page, and then again through an axis through the middle. So I'll draw a second copy of the same diagram. Okay, that's not exactly the same length, but it'll have to do. So through that axis and then through that axis. Calculate the net torque in either case, and they have some forces on this diagram that I will copy over. So, oh, that's not good. So they said the length of this thing is 4 meters, and I'm already failing to demonstrate good practices here. You want to try and write these a little bit lower because you're going to need the space. A lot of times you're going to need some space for these drawings. They get really crowded, and even worse if you use the proper definition of lever arm, at least in my opinion. So they've drawn a force over here, and they said this force is 30 newtons, and they made this angle 45 degrees. They've drawn a force 2 meters from the end, so they've drawn a force over here at 2 meters from the end, and there's a force here of 25 newtons, and it is at an angle of 30 degrees with the vertical. And they've got one last force over here, and it is at an angle of, I'll draw a horizontal dotted line there, it is at an angle of 20 degrees. That looks like 220 degrees. Here, let me make the 0 bigger. Yeah, that's a little bit more readable. 20 degrees with the horizontal. This is a 10 Newton force. Maybe I should have written the angles in a different color. But oh well. And it's going to be the same diagram for this one, except that the pivot is at the center instead of at the left end. So this is going to be your 2 meter mark. And then the full length is 4 meters. Not the same scale as the other drawing, but yeah. And then those same 3 forces, the 25 newtons, the 10 newtons, and the 30 newtons. And let me wall these off from each other. There. Okay, so calculate the net torque for each scenario. That's all we need to do here. And of course, give its direction, which we will simply give as clockwise or counterclockwise. So for clockwise, we can abbreviate that as CW. So CW is clockwise. Whereas CCW is counterclockwise. 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 Anti-clockwise for some of you. Whatever you prefer to call it. And whether you want to consider clockwise or counterclockwise to be the positive direction is completely up to you. I tend to just pick based on the problem I'm given. Usually, I tend to see a lot of problems where everything is already moving clockwise, so I actually go against convention and pick clockwise as the positive direction more often than not. But if I see that an object is going to spin in the counterclockwise direction, then I'll use that as the positive direction instead. And if I'm not sure, I'll probably just default to whatever is the first force that I look at, whatever direction its torque is going to be, that's probably what will determine my choice. I wouldn't spend too much time trying to decide because, you know, you're wasting precious seconds there, and on an exam, those seconds count. Let me take a sip of water before I start this problem. Okay, that feels a bit better. And let's go ahead and net those torques. So, what I like to do when trying to calculate net torque, no arrowhead, I'm just doing magnitude for now, and I guess there will be a sign to this, a positive or a negative. Yeah, okay, yeah, then I guess it does make sense to have an arrowhead after all. Anyway, so what I like to do with these net torque problems is I like to start from wherever the pivot is and work my way from one end of the object to the other. Or sometimes if the pivot is not at the end, like over here, I'll still start from one of the ends of the object and move my way left to right or right to left or top to bottom or bottom to top, as the case may be. We will see situations where it's not always left to right. We'll see situations like we will have something like a ladder propped up against a wall, and for that I would just go from the bottom of the ladder to the top or from the top to the bottom. It doesn't really matter, but it's good to stay organized in that way because it prevents you from missing any torques that you might have along the way. It's a good way to just make sure that you catch everything. So over here, starting from the left and moving over to the right. Starting at the left, the first force I encounter is, well, right at the pivot. So that's going to be R is equal to 0 times force is equal to 30 times, I guess the angle would be 45 degrees, so sine of 45, not that it matters because we're multiplying by a 0. Okay, and then I continue moving and moving and moving along this beam, and next thing I encounter is at R equals 2 meters away from the pivot. So that's going to be 2 meters away from the pivot, multiplied by a force of 25 newtons. And that's going to be at an angle of, well, let's see, it says 30 degrees, but that's 30 degrees with the vertical. It's not 30 degrees with the beam. If I were to draw my R vector, if I were to draw the vector R, my pivotal displacement from the pivot, it would look like this. So the angle that I actually want is this over here, which would be, depending on how you look at it, it can either be 60, or if you look at it from this side and take all that, that would be 120. Does it matter? No, we already talked about that. Sine of 60 and sine of 120 are the same thing. In fact, that was the one that we demonstrated on the calculator. So it doesn't matter what you write here, sine 60, sine 120, as long as you don't write sine of 30. Be very careful about that. You need to really be on top of your geometry when doing torque. Any geometry mistake could cost you the whole problem. And now for direction, positive or negative. I'm going to go ahead and call this a positive torque. And what direction is this, clockwise or counterclockwise? If you can't immediately see it, you'll get there with enough practice, but for now, what I would recommend is just take your pencil and try to imitate what you're seeing. So hold it down wherever the pivot is supposed to be, and then try and apply the force. And I see that my pen swung counterclockwise, so I know this is a counterclockwise torque. At least for this pivot. That might change once we look at the other pivot. So yeah, counterclockwise I'm going to consider positive for this problem. And then next up, so we've done first force, which had no torque, second force, which has positive torque, third force I encounter, and it's the last force as I go along this beam, is this 10 Newton force at a 20-degree angle to the horizontal. It's also at a 20-degree angle to the pivotal displacement. So, wait, that's the wrong pen. So, it's going to be 4 meters times 10 newtons times sine of 20 degrees. The pivotal displacement is straight to the right. The 10 newtons is at that angle. The angle between them is 20 degrees, or depending on how you look at it, 160. Which is the other example that I showed on the calculator. Wow, how ironic is that? I've never even done this problem with a student before. I don't think I've ever done this problem in my book before. What I'm trying to say is I didn't plan this. Those were just the examples that came to mind. I didn't pick those numbers so they would fit this problem, but there you go, one of those funny coincidences. And what is the direction of this torque, clockwise or counterclockwise? It looks like, again, you can just grab your writing utensil, hold it down wherever the pivot's supposed to be, and try applying the force. And I see that causes it to swing clockwise. Since we already declared counterclockwise to be positive, clockwise must be negative. And now we just bring out our calculator, and the rest is history. So that's all just going to be 0. We can skip that one. 2 times 25 times sine of 60. So 50 times sine of 60 degrees is 43.3, and then minus 40 times sine of 20. Oops, forgot my multiplication sign there. Okay, and after all the subtraction is done, I end up with a total torque of 29.62. 29.62 what? The units for torque are Newton meters, which might sound familiar. Wait a minute, Newton meters. Newton meters. Where did we encounter Newton meters before? We encountered them when discussing the topic of work and energy. Work was force times displacement I guess I'll call it delta, what do I want to call it? I guess we'll call it delta x. Force times displacement times cosine of the angle between their directions. So we took newtons and we multiplied them by meters. Well, here we took meters and multiplied them by newtons. So wait a minute, does that mean that torque is in joules? No, it does not. Torque is a vector. The torque Newton meters, because it's a different kind of multiplication, it's not equivalent to a joule. These Newton meters are different from these Newton meters. It's a different kind of multiplication. You have to keep this written as Newton's dash meters or Newton's dot meters, whatever you want to use to represent it. Usually in textbooks I think they use the dash, but I've also seen the dot symbol used. But yeah, you have to keep it as Newton meters. You can't just condense it into joules. It wouldn't make sense. Torque is supposed to be a vector, joules are units for a scalar. So definitely don't make that mistake. I mean, you can still expand the newtons into kilogram meters per second squared if you wanted, but you can't multiply these meters into whatever you turn your newtons into. So just keep that in mind. Okay, next part B. So we're going to do the same thing again, but this time with a different pivot. So starting from the left, I've got, it's 2 meters away from the pivot this time, instead of 0 meters, and it's still a 30 Newton force. And the angle is going to be 45 degrees because my pivotal displacement, I'm so glad I came up with that term. This makes things so much easier to explain. I don't have to describe it with, word salad every time I want to talk about it. So the direction of your pivotal displacement is along that way. Your 30 newtons is in that direction, so the angle is just going to be the angle with the horizontal. It's going to be the 45 degrees. So that's times sine of 45. I know some of you can already see that, but it's good to cover that because even when you are good with your geometry, sometimes when you're trying to take in new concepts at the same time that you're applying old knowledge, you can benefit from slowing down a little bit and being careful. Okay, next force we encounter as we move from the left end to the right end, I get to here, and now I'm encountering this 25 Newton force. How far away is it from the pivot? Well, it's at the pivot, so 0. Plus, minus, it doesn't matter, but I'll say plus 0 times 25 times, I guess that would be, if there was some non-zero displacement, it would be in a horizontal direction. And the angle with the horizontal is 60 or 120, depending on how you want to look at it. And then we have, I forgot to specify. So that first torque, is it clockwise or counterclockwise? Let's see. If I hold the pen down here and I pull at a 45 degree downward angle like this, I get counterclockwise motion. So yeah, that'll be positive. Since we decided counterclockwise is positive for this problem. let's see, so that's first torque taken care of, second torque is 0, we don't have to worry about direction, and third torque, if I continue moving, then I encounter a third force, and the third torque is going to be what? Well, pivotal displacement is going to be 2 meters away from the center, and it's going to be in a horizontal direction, so angle with the horizontal, that was the 20 degrees, so we've got 2 meters, so R, and then F. I mean, it wouldn't matter if I wrote the 10 first and then the 2, but I want to try and keep things in order so that we remember that it's R cross F and not F cross R. It might not matter for the AP exam all that much, but if you decide to do more physics in college and you decide to use your AP credit to skip over to the next course, your college professors will expect you to know how to do things like the right-hand rule and whatnot. Actually, they'll expect you to know how to do some other things too with vectors that we don't really do in any of the AP Physics courses. You might learn that stuff if you take the topic of vectors in pre-calculus, but if your pre-calculus teacher doesn't choose to cover that unit, then you will probably want to read that unit in your textbook on your own, just so that it's not completely foreign to you if you end up having to use that stuff in a college physics course. Anyway, 2 times 10 times sine of 20 degrees was the angle. And this is clockwise, right? Because if I hold it at the middle and I apply a force at an angle like this, that'll cause clockwise rotation. And clockwise is negative for this problem. Okay, calculator time, that's a 0, so I can skip it. So we've got 2 times 30 is 60 times sine of 45. And then that's going to be minus 20 times sine of 20. And I'm getting a total of positive 35.586, or 35.59. I'm getting 35.59. So positive in both cases. They did ask for the direction, so counterclockwise and counterclockwise. If my answers had come out, if either of my answers came out negative, I would just give the absolute value and write clockwise on it instead of counterclockwise. So basically the same thing I always recommend. Specify direction in words, not with plus and minus signs. Because plus and minus signs are only useful when there are only 2 possible directions, but words, describing directions in words will work for higher dimensional situations. Whether it's 2D or 3D. When there's 3 or more directions, specifying in words will prevail. Alright, that problem is done. So now, let's have a look at an equilibrium problem. Alright, this problem says, a window washer is standing on a scaffold supported by a vertical rope at each end. The scaffold weighs 200 newtons and is 3 meters long. What is the tension in each rope when the 700 Newton worker stands 1 meter from one end? I will read the problem again, but let's draw the diagram first. Well, draw a diagram. saying draw the diagram implies that there is one in the book, but there isn't. It's just a description with no drawings. So we have a scaffold, which is just some sort of platform to stand on. And the window washer is standing on it, and it's supported by a vertical rope at each end. So there are two ropes. I'll call this force of tension left, and I will call this force of tension right, and I should probably use a different color for it. Yeah, let's use a different color for force. Let's use something darker. How about green? There we go. Force, tension, right, and force, tension, left. And what else did it say? The scaffold weighs 200 newtons and is 3 meters long. So the length is 3 meters. I'm going to draw it all the way down here so that I have enough space. And the scaffold weighs 200 newtons, so that's going to be at the center of gravity, which is going to be right in the middle. Just assume that objects are going to have a uniform mass distribution. Assume that they are objects of uniform density and that their center of mass or center of gravity is going to be at their geometric center, unless the problem tells you otherwise, which if you're in Physics 1, it won't. At least it shouldn't, because you're not supposed to know how to do that. If you're Physics C, we will talk about that later. We'll talk about some of it at the end today, and the rest of it will be like after we're done covering the final chapter for Physics C, which is going to be the chapter after this, actually. So we're not too far off. We're not too far away from the calc-based revisit of topics for the Physics C students. I'm sure some of you have been on the edges of your seats waiting for that moment. Now, where was I? 200 newtons. That's force gravity. I'll call it force gravity S for scaffold. And then the worker, who is 700 newtons in weight, stands 1 meter from one end. It doesn't matter which end, just pick one. But also, since we're here, I should go ahead and specify that this is 1.5 meters, right? It's at the geometric center of the object, so make sure you note that it's 1.5 meters from each end for the weight of the scaffold itself. And then for the worker, let's draw them over here, for example. And they weigh 100 newtons. So some people will draw the weight of the worker onto the scaffold, the beam, whatever you want to call it, which does get you the right answer, but conceptually it's wrong. So I know this might feel like silly extra work, but I think it's important to make sure that you properly master the concepts of force and understand what is actually going to be pushing down on this beam. So this worker has a weight of 700 newtons that pulls down on him. The 700 Newton weight acts on the worker, not on the beam. Also, if he's going to be supported by the beam, a 700 Newton normal force will act upward on him so that he is in equilibrium. But if there's a 700 Newton normal force upward on him from the beam, then there is a 700 Newton normal force downward acting on the beam from him. And I guess I don't really have enough space to draw this with proper scale. Actually, yes, I do. I can just draw it from up above like this. That's going to be force normal equals 700 newtons. And this is what generates a torque on the scaffold. This is the force that's acting on the scaffold. So we can now remove the worker from the problem. We can just remove him and the two 700s that act on him and leave that out of the problem. All we need are the forces that I drew in green. Also, distance. So he is at, see, this is why, and apparently I didn't start low enough, but there you go. So this is why I say try to start really low, and probably lower than you think, because even here, with me thinking I was being extremely careful, giving myself enough space, it wasn't enough. So draw your distance indicators, whatever you call these, draw them pretty far below the rest of your diagram so you have enough space to squeeze all this in there, because these diagrams, like I've said, what, 4 or 5 times now, these diagrams get really crowded. And some people insist on using the official lever arm approach, drawing action lines for their forces. Okay. I suppose you're free to pick your poison. I mean, the fortunate thing with this problem is that everything is already perpendicular to the scaffold, so you wouldn't actually have to draw any action lines if you were taking that approach. Everything would just be, would already be perpendicular to, all of your R's would already be just horizontal. So yeah, you wouldn't have to do anything too fancy. You wouldn't have to mess up your diagram too much. But we'll see problems where it could get ugly for those who use that method. Anyway, so equilibrium conditions. This scaffold is supposed to be stable. This worker is supposed to be able to stand on the scaffold and do their work without risk of falling, without risk of the scaffold tipping over while they stand on it, without any of that. So these ropes better be able to withstand whatever amount of tension is needed from them. So the following conditions must be true. We'll have to work backwards and figure out how they are true. But net force X needs to be 0. Easily fulfilled because there are no horizontal forces here. So check. Net force Y must be 0, which tells me that forces up on the beam, not the worker, on the beam, or what was it called, the scaffold, that's force of tension left plus force of tension right, those are the two upward forces, minus the forces downward, so minus force of gravity scaffold, or I guess I can just call it force of gravity. Okay, I'll call it force of gravity scaffold, and then minus the normal force that the worker exerts downward on it. So that's going to be force of tension left plus force of tension right minus 200 and minus 700 equals 0. Or tension left plus tension right equals 900 if you move those over to the right-hand side. So that's one condition that needs to be met, or rather that already is met, assuming that this scaffold is already stable. And then the other condition is that the net torque needs to be 0 around any pivot. around any pivot means I can pick whatever pivot I want. And I know that the net torque is going to be 0 around that pivot, because if there were any pivot around which the net torque was not 0, then this scaffold and the worker on top of it would already be rotating around that pivot. So the fact that they're not rotating means no such pivot exists. So I can pick wherever I want. So much freedom, so much choice. But there are smarter ways and not so smart ways to use that freedom. Freedom is not entirely free, after all. So you need to be strategic about where you place your pivot. The powerful thing about pivot placement is that where the pivot is placed, any forces at that location will have their torque rendered meaningless. They will have no torque if they are applied at the pivot. We saw that earlier over here. When the pivot was on the left end, the force on the left end had no torque. When the pivot was at the center, the force that was acting at the center had no torque. So, if I use this wisely, I can eliminate one of my unknowns. And reducing the number of unknowns in my equations, that is a big deal. If I can eliminate one unknown, or better yet, we'll see situations where we can kill off 2 unknowns at the same time just by our choice of pivot. If I can do that, then I probably should. So, the best choices here would be to place your pivot either on this left end or this right end. Either one of them will work. Either one will work. In fact, if you do it on the left end, you can write one equation and then do it again and write another equation for the right end. Those equations are not going to be independent of each other. If you try to pick multiple pivots and generate multiple equations from them, putting those equations together is not going to yield any new results. Those equations are not independent of each other. So be very careful about that. I always mention when talking about problems with a lot of unknowns in them that you need just as many independent equations as you have unknowns. The freedom to generate basically an infinite number of equations with this might get you thinking that you can do more with it than you actually can. The equations generated by this net torque equals 0 requirement, they are not going to be independent of each other. Once you've generated one, generating others will not give you any new information. Anyway, I will just go ahead and put my pivot on the left because the right side is looking rather crowded over there. So yeah, I'll just put my pivot over here. And since that is my pivot point, let's go ahead and start writing down our individual torques. So torque due to tension left is going to be lever arm, or not lever arm, pivotal displacement. Or I guess this is also technically lever arm in this case because it's 0. And also because all the forces are vertical and all of the pivotal displacements are perpendicular to the vertical direction. So yeah, in this case all my pivotal displacements are lever arms, so it doesn't really matter. I can use the terms interchangeably for this problem specifically. But 0 times whatever force of tension left is times sine of 90 degrees. I know writing sine of 90 when it's equal to 1 might feel kind of redundant, but it's good to just do it anyway to reinforce the habit of making sure you include the angle when calculating a torque, because you get used to problems where the force and pivotal displacement are perpendicular to each other, and then you end up getting used to not writing the sign of the angle, and then you hop onto a problem where the angle actually matters, and you forget it, and then you ruin your whole problem. Let's avoid that. Let's try and develop good habits from the beginning. If you start off with bad habits, then trying to correct those bad habits will be more work than just developing the right habits from the get-go. Anyway, moving on. So if I continue moving from left to right, the next force I encounter is right over here. It's going to be the 200 Newton gravitational force, and it's going to create a torque where if I'm holding this thing down here and I'm pushing down on it this way, it'll swing clockwise in the absence of all the other forces and their torques. I'm going to say clockwise is positive for this problem. So let's say clockwise is my positive direction for this problem. I should have done that for the previous problem, come to think of it. For the previous problem, I did counterclockwise was positive. Anyway, we'll say it's positive, and it is how many meters away from my pivot? Well, it's at the center, so it's 1.5 meters away, times the force is 200, times the angle, R is going to be this way, force is going to be straight down, that's going to be 90 degrees, so sine of 90 degrees, which is equal to 1. Next force, so continue moving to the right. The next force I encounter is this normal force, which is acting downward. So if I hold down my pivot here and I push on the object this way, it will rotate clockwise, so positive, and then it is at, let's see, so the whole beam, the whole scaffold is 3 meters, and the person's normal force is where he's standing, is 1 meter away from one end. So 1 meter from 3 meters, that means we're 2 meters away from the pivot at this point. So this distance, I guess I'll write it over here. So that is 2 meters away. Pivotal displacement is 2 meters, and then normal force is 700 newtons, and the angle is going to be 90 degrees. Pivotal displacement is just from left to right, straight to the right. Normal force is straight down, so that's 90 degrees between them. And then finally, this one better be a minus, otherwise there's no way this net torque will be 0. If I continue moving to the right, the final force I encounter on the scaffold itself is this force of tension right. It pulls upward. Since the pivot is here, an upward pull would cause a counterclockwise rotation, which will be negative, since we already decided clockwise is the positive direction. So that's negative, and then that is at a pivotal displacement of 3 meters away, the full length of the scaffold, times force of tension right. We do not know its value yet. And let's see, times sine of 90 degrees. Since pivotal displacement is going to be just straight to the right, and tension right is straight up, right and up are 90 degrees apart. So that's sine of 90 degrees, which is 1. Okay, so that whole thing is just going to go to 0. That whole thing is just going to go to 0. 1.5 times 200 times 1, that's going to be 300. That's going to be 1400. So 300 and 1400, that's 1700. Minus 3, force of tension right. So we've got 0 equals 1700 minus 3 force of tension right. So add 3 force of tension right to the left-hand side. Divide by 3, 1700 over 3 is 566 repeating 6s, I'll say 566.67. So force of tension right is, 566.67 newtons. And then they wanted the force in the other rope. So now that we know force of tension right, the easier way to do this, one way you could do this is you could just pick another pivot and write another net torque equation and plug in this for force of tension right and solve for force of tension left that way. But the easier approach would probably be to just go ahead and use one of your net force equations, in this case the only net force equation that actually has anything meaningful in it. So tension left plus tension right minus 900 is equal to 0. So I'm going to go ahead and take this and do force tension left plus force tension right is 566.67 equals the minus 200 and minus 700 added to the right hand side gives me 900. 900 minus 566.67 is 333.33. So force of tension left equals 333.33 newtons. Do you suppose this has anything to do with the fact that the man chose to stand a third of the way between the two ropes that we're getting these 0.67 and 0.33? Let me think here. So the total force that the ropes have to support is 900 newtons is 900 across both of them. And when the man is standing closer to the rope on the right, I would expect the rope on the right to have more tension in it. I would expect the rope to be tighter where the man is standing close to and looser where the man is far away. And that does seem to hold true. Tension right is greater than tension left. So intuitive check, it checks out. As for the actual ratio between them, well, I think the fact that the man is basically taking his own weight with him wherever he stands makes this not super intuitive, but basically these two tension forces, they will share the weight of the beam itself equally. So there's 100 here and 100 here to support just the weight of the beam. And then for the remaining 700 from the man, that 700 is going to get distributed unevenly. So it's going to be, since he's 1 meter away from tension right and 2 meters away from tension left, then tension right is going to get, since there's a 1-to-2 ratio of distances between the two ropes and the man, there's going to be a 2-to-1 ratio between how much of the man's weight, or rather how much of the man's normal force, those two tensions will counter. So the one on the right, since it's twice as close, will have to support twice as much of the 700. So if you split it 3 ways, then tension right will get 2/3 of the 700. So 2/3 of 700 plus the 100 that it has to support from the weight of the scaffold itself. 2/3 times 700 is 466.67 plus the 100. There you go. That's the 566.67. And then 1/3 of 700, which is 233.33, plus the 100 that it has to support for the scaffold. That's your 333.33. So that's just a little bit of intuition. You don't need to do it that way, and I would not advise that you try to learn to do it that way, but it is a little extra if you can practice doing that, at least for these simple problems where everything is either strictly vertical or strictly horizontal, and you don't have to worry too much about angles throwing a wrench in things. If that's something that you have the free time for, if you practice everything in this chapter and you feel like you've properly mastered it all and you're just looking for something extra to do, then you can try and play around with this idea and see if you can use it as just one additional way to check your work and potentially catch mistakes. But I would not make it the first priority to try and learn doing what I just did there. Next problem. What do I want? I know I've done some of these in an old video. But they're such good problems that I don't actually, you know what I can do? I can just look in the other book, because I haven't recorded many videos involving problems from the other book yet. Yeah, let's see what we can find in here. The problem with this other book is that sometimes they expect you to do calculus stuff, so I'm going to try and avoid that if I can. Let's see, torque problems. Okay, here's one. And let's get a new sheet for this. Wow, it's already 2 hours. Well, almost 2 hours. So I guess my prediction wasn't that far off about how torque would be taking up the majority of this session. Okay, where did the problem go? There it is. So it says a diver of weight 582 newtons stands at the end of a uniform 4.48 meter diving board of weight 142 newtons. The board is attached by 2 pedestals 1.55 meters apart, as shown in the figure, which I will draw for you. Find the tension or compression in each of the 2 pedestals. Tension or compression, meaning that the 2 pedestals have the option of either pushing or pulling on the diving board. That is important. And yes, they did use the word tension there, because tension is not just for ropes. Tension is not just for ropes. If I pull on my arm, then I feel tension in my bones. I feel tension in my arm if it gets pulled on. So yes, rigid objects that are still solid and don't go slack in the absence of some pull can still exert a tension force. It's just that usually when we think of tension, we think of things like ropes. But yes, you can absolutely have tension in objects that aren't very rope and string-like. So they have this diving board, and then it's attached to these two pedestals, which are 1.55 meters apart. Okay, so that distance, I'm going to draw it all the way down here. Hopefully this will be low enough. So that is 1.55 meters. I guess I'll write it over here. 1.55 meters. That's the distance between the two pedestals. And then the whole entire board itself is 4.48 meters. 4.48 meters. And if you subtract, you can figure out what this distance is in case it matters. You can just do 4.48 minus 1.55. We'll calculate it if it ends up mattering. And then we've got the diver stands over here at the edge of the diving board. And it says the diver has a weight of 582 newtons. We've already been through this. If they have a weight of 582 newtons pulling downward on them, then the board has to exert a 582 newton normal force upward on them, which would then mean that the diver in turn exerts a 582 newton downward normal force on the diving board. And this is the force that we're going to calculate a torque from. Anything else mentioned in here before we start? Nope. Find the compression or tension in the two pedestals. So this is another completely vertical problem, at least as far as the forces are concerned. So these pedestals, they could either exert a force up or down. We don't know yet. I mean, at least one of them has to be up in order for the net force Y to be 0. If all forces are pointing down, then that's not going to work. Net force X is 0 because, well, there are no forces in X, so we can just check that off. Nothing useful is going to come from using that equation here. Net force Y has to be 0, so what am I going to call them? What am I going to call them? I mean, I guess one of them would be a normal force and the other would be a tension force if one of them pushes and the other one pulls, but I don't know which is which yet. So I'm just going to call them force left and force right. And let's assume they're both up for now. I'm going to call this force left, and I'm going to call this force right. And of course, don't forget the weight of the diving board itself. So they said the diving board weighs 142 newtons, and if it's 4.48 meters in length, then half of 4.48 is 2.24. So somewhere around here-ish is 2.24 meters. And then we have to calculate the gap. Well, actually, we might not have to. We might not have to calculate the difference between 2.24 and 1.55. But force of gravity, and I'm not drawing my vectors to scale here, but force of gravity on the board is 142 newtons. Okay, so net force Y is going to be 0, is going to be force left plus force right. Whoops, that's not an F. There, now it's an F. Force right minus 142 and minus 582. And for those forces in orange, those are the net force Y on the diver and not on the board, so they don't belong in this equation. This is net force Y of the diving board, specifically board. That is not very readable. The O and the A got smeared together, but you know what I'm trying to say with that. Anyway, other information, it doesn't look like we have any. So it's just asking us to find those two forces. So we need to take advantage of our third equation. Net torque needs to equal 0 around any pivot, which means I should be able to just pick a pivot, and whatever pivot I pick, the net torque around it should be 0. If it's not, then equilibrium just wouldn't be possible in the first place. So where do I want to pick a pivot? Well, if we're feeling adventurous, we can put it over here. But then we would actually have to calculate this distance, which, I mean, it's pretty easy to do. You just do 2.24 minus 1.55, but if you wanted to save yourself that step, then just putting your pivot on the left again would be the better choice. I'll go ahead and just do it over here, just so we can have some variety in our examples. But if I were just doing this for myself on a test, I would just pick the left end because it would be easier. But just for the sake of variety, we'll do the slightly more time-consuming one. So I'm going to place my pivot over there, and I'm going to decide on a positive direction. Let's do clockwise as positive this time, because I see the first torque I'm going to calculate is going to be clockwise. Let's make that the positive. So force of tension left times, let's see, pivotal displacement from the pivot to force of tension left, that is just going to be 1.55 meters, and then left and up, the angle between them is 90 degrees. So we've got 1.55 meters times force of tension left. I guess I don't really need the parentheses for variables, but force of habit, and then times sine of 90 degrees, and that is going to create a clockwise torque. If I hold this thing down and push up on it from the left side, that'll cause clockwise rotation in the absence of all the other torques. So I'm going to make clockwise my positive direction. Next thing I encounter as I go from left to right is the force right, which is at the pivot, so it'll be just 0. So plus, minus, it doesn't matter. 0 times force of tension right. Or force right, not tension, just force right. Muscle memory from the previous problem. And then times, I guess it would be sine of 90, but it's going to be 0 overall, so doesn't matter. And then next force I encounter is going to be the force of gravity. If I hold the board down over here and push down on it from the right of the pivot, that will cause a clockwise torque. That's going to be positive. Oh. Well, I think we just discovered which of the two pedestals is actually going to be pulling. Because if this force is down on the right side of the pivot, and that normal force over there is also down on the right side of the pivot, then that would mean all of our torques are clockwise, which wouldn't make sense. So that's okay. If we just continue with this equation, we're going to get a negative for a force left, which I also somehow ended up calling a tension force. Sorry about that, I just caught it. So yeah, force left is going to come out negative, which just means that I got its direction wrong. That's okay. The math still works out for us in the end. I just have to correct my diagram later. Anyway, so it'll be plus, it's not 2.24. It's how far from the pivot. It's 2.24 minus 1.55, which is 2.24 minus 1.55 is 0.69. 0.69 meters away. So 0.69 times 142 times sine of 90 degrees, because it would be right for the pivotal displacement and straight down for the force. The angle between them is 90 degrees. So that sine of 90 is just going to be equal to 1, and it's not going to change anything. And then finally over here, 582 at a pivotal displacement of how much? Well, I guess we need to do 4.48 minus 1.55. More extra steps. So that's 2.93. So this was, I'll go ahead and write it, was 0.69. And this, and that's in meters. And this is 2.93 meters. And yeah, 2.93 meters from our chosen pivot times 582. And it's going to cause a clockwise rotation, so positive. So plus 2.93 times 582. And since I don't have enough space for it, I'm just going to say times 1. Times sine of 90 degrees, which is 1. I'll just write the times 1 since we don't have the space. Okay, and all that is supposed to equal 0, so if I subtract 1.55 force left on both sides, then I get negative 1.55 force left equals, let's see, that's a 0, and then those are just in the calculator. So 0.69 times 142 plus 2.93 times 582. And that's 1803.24, 1803.24 Newton meters. Divide by negative 1.55, and I get negative 1163. Force left is negative 1163.38 newtons, or in other words, 1163.38 newtons of tension. That is this was wrong. The actual proper direction of the force on the left is this way. That's what the negative sign means. As long as we're consistent with all of our other choices of sign convention, if something comes out negative, then it's negative according to our choice. And our choices were up is positive, and clockwise is positive, and all that good stuff. I guess this negative over here would actually come from... This negative means counterclockwise. It doesn't mean down. Yeah, because clockwise and counterclockwise has nothing to do with the positive versus negative direction for the force. Be very careful about that. You can have an upward force cause a clockwise torque or an upward force causing a counterclockwise torque, depending on where that force is applied relative to the pivot. An upward force to the left of the pivot will cause clockwise motion. An upward force to the right of the pivot will cause counterclockwise torque. So, yeah, the positive and negative from clockwise versus counterclockwise, do not confuse it with the positive and negative from up versus down. They are completely unrelated. So if your negative sign is coming from having the opposite rotation direction, then you need to determine the direction of the force based on the direction of rotation that it would cause, not based on what you decided was the negative direction for your forces. Be very, very careful about that. And I guess, are we done? No, there's one more force to find. What am I saying? Are we done? No, we're not done. Okay, so because force left has to cause a counterclockwise torque, which requires it to be downward, that also means that force left needs to be substituted as a negative in our net force y equation. So it's going to be negative 1163.38. I'll do it up here. 0 equals negative 1163.38 plus force right minus 142 and minus 582. All that equals 0, so just add all these over to the left and we get force right. Simple addition. 1163.38 plus 142 plus 582, and that's 1887.38. So that's going to be 1887.38 newtons equals force right. That is going to be compression or normal force. And that one has to be up because all the other forces are down. But if there was any reason why it could be down or up, then what we would probably have to do in that scenario is pick another pivot and write another net torque equation and see what direction of rotation it would have to have based on whether it ends up with a positive or negative sign, very much like what happened with force left over here. Okay, that was a pretty good problem. Now let's see what else there is to see. give me some time to read through these and see what's good. Oh, this might be a good one. Hold on, let me read through it. Ooh, okay. Let's work with this one. So it says, well, let me draw the diagram first before I actually read it, since it is probably easier to understand when you actually have the diagram to look at. So they've drawn a triangle ABC. So you've got a wall, and then you've got some sort of mechanism here, some sort of hinge. And you have a bar sitting horizontally like this. So you've got point B, point A, and then at point C, there's a rope attached. Or is that what they called it? A thin wire is what they called it, a wire. And then there's a block over here. And this block is free to move around, so they slide it left and right. And then this distance over here, they call this distance x. Okay, so it says a thin horizontal bar, AB, of negligible weight and length L is pinned to a vertical wall at point A and supported at point B by a thin wire BC that makes an angle theta with the horizontal. So this angle over here, let me use a different color for it. This angle over here, they called it theta. A weight W can be moved anywhere along the bar. That's this thing over here. They just gave us its weight W. Normally I would just call this force of gravity, but fine. I will use their notation this time. So force of gravity, they called it capital W here. I hate that because we already use capital W for work, but we can live with it. So a weight W can be moved anywhere along the bar as defined by the distance x from the wall. Part A, find the tension T in the thin wire. So they called the tension in the wire capital T. I would rather call it F sub T, but okay. Because we also use capital T for period. That was the previous chapter. And also it's going to come up again in the next chapter. So brace yourselves for that. So find the tension T in the thin wire as a function of x. And then part B, find the horizontal and vertical components of the force exerted on the bar by the pin at point A. Okay, so it's a pin, not a hinge. Well, I guess I need to look up the proper definition of what a hinge is. Because when I think of a hinge, I think of, you know, something that has parts that can swing open and shut, like the hinges of a door. And a pin would imply, well, I mean, you could have a pin holding a hinge together, holding the two parts of a hinge together. But now I'm splitting hairs. Anyway, find the horizontal and vertical components of the force exerted on the bar by the pin. And then for part C, they give you some numbers to plug in. And they ask you to find the maximum distance x before the wire breaks. If the wire can withstand a maximum tension of 520, and I'll give the other numbers once we get to that part of the problem. So first part was find the tension in the thin wire as a function of x, and the length of the bar was L. I don't think I drew that far enough below, but we'll see. Actually, no, there's only one other distance we need to account for here. Well, two. X and potentially L minus X, but we'll see. So yeah, find the tension in the thin wire as a function of X. So there's two more forces that we need to put on this diagram, and they did actually mention them. I'll use this same color over here. So they said they were the forces at the pin. So I don't think this tension is going to be enough to support this weight on its own, so I assume that over here at the pin there's going to be an upward force. I could be wrong, it could turn out to be downward. You just have to make a guess. We did the same thing with the previous problem. We guessed that FL was up, turned out to be down. It's okay, just pick something. So I'm going to call this, what, force Y is what I'm going to call it. Some people also call it force R, like capital R for resistance or something like that, which is also fine. And then there's also another force over here. This pin is actually going to exert a force in some sort of diagonal direction, I would assume up and to the right, although it could also be down and to the right. But there has to be some force to the right because this tension has a leftward component, and the net force along the x direction has to be 0, so there has to be some horizontal force to the right to cancel that out, and that would have to come from this hinge point, or this pin as they called it. So there's also an Fx over there. If you think about it, it kind of makes sense. If you try to, what would be a good demonstration here I could give? If you try to hold something against yourself, so if I were to take this calculator and hold it just with my fingers, and instead of supporting its bottom with my other hand, if I were to hold it against my chest, which isn't something I can conveniently show on a document camera, but if you are to believe me here, I'm just holding it against my chest. I can't really, I can't go that far under the camera. But, well, let's do this. If I hold it like this, yeah, there we go. So that's basically what I'm doing. So I'm just pushing its bottom against, I was pushing the calculator's bottom against my chest to hold it up. So if you do it with just the back of your other hand, you feel the back of your other hand exerting some force, pushing it away. So this Fx would be the normal force from the pin just pushing away, because this wire is basically trying to pull this bar into the pin. The pin is trying to resist that, so it pushes back against it and pushes it to the right. And then I guess the pin is also acting as some sort of, let me grab, What can I use? I can use this pencil. So think of the pin like this, where the pin has to exert some sort of upward force, because if it doesn't, then this ruler is going to bring it down. So imagine this ruler is acting as the bar. The pin has to exert some upward force, or I suppose it could be some downward force, because if the tension pulling up on the bar is really strong, there could be some excess upward force from that wire, from that tension force. And in that case, the ruler might be, or the bar rather, might be getting pulled up too far, right? Too far up, in which case the pin is actually having to resist from its bottom side and push down. So that would also be a normal force then. That would also be a normal force, because it's just the bar pushing against the pin, whether it's upward or downward. The bar is pushing against the pin, and the pin is pushing back against the bar. So yeah, both of those forces from the pin would be normal forces. Where was it? I think that's where it belonged. Sorry, if I don't put my stuff away immediately, I'll probably forget where it goes. Well, the stuff that I don't pick up regularly anyway. The consequences of being a neat freak. Now then, with all that specified, I think we can go ahead and write, or at least try to write, an equation for the tension in the wire as a function of x. Find T of x. That's part A. Find T of x. Okay, so if we want this to be in static equilibrium, then net force in the x direction has to be 0, net force in the y direction has to be 0, and net torque rather, has to be 0 around all possible pivots. Okay, net force x having to be 0, that means that tension times, well, that means that Fx, I'll say right is positive, minus, it's going to be tension cosine theta, minus T cosine theta, that has to be 0. For net force y, we would have tension sine theta is definitely upward. I'm going to say plus Fy, although Fy could turn out to be negative in the end. We'll see. And then minus W. And we'll deal with that later. And then net torque equals 0. Should be 0 around any pivot, which means we are free to choose whatever pivot we like. Best choice of pivot would have to be at the pin, because there are two unknown forces acting at the location of the pin. So if we place the pivot there, then they will both come up as zeros in our net torque equation, which is a great way to eliminate variables from your equation. So I am going to pivot at the pin. That's probably not a good color to use for that. Let's use this color instead. That's a little darker and more visible. So that is where I am going to pivot. Okay, torque due to force X is going to be a 0, plus torque due to force y is also going to be a 0, both due to the pivotal displacement being 0. And then next up, we're going to have at some pivotal displacement x, we have the force W. So we've got x times W times sine of 90 degrees, right? The pivotal displacement is going to be straight to the right. W is going to be straight down. It's actually not W itself that applies to the beam, but a normal force of magnitude W, just like the previous problems where we took the weight of the person standing on the surface, got canceled out by a normal force, but also exerted an equal normal force downward on the beam, scaffold, what was this called? Board, whatever you want to call it. But yeah, a normal force of magnitude W downward multiplied by a pivotal displacement of x multiplied by sine of 90 degrees, which is 1, of course. And then clockwise or counterclockwise, this is going to be if my pivot is here and a normal force downward is exerted on this bar, then it should result in clockwise motion. And clockwise, I think I'm going to actually make it negative here. I'm going to say that counterclockwise is my positive direction for this problem. And that's because I want T to come out positive. So that's actually the last force here. They said that there was negligible weight for the bar itself, so no force of gravity this time. So that just leaves the tension force, which is at a distance of L. So that's going to be, it has to be plus, because the only other thing here is a minus and the total needs to be 0. So plus L times T times sine of, let's see, so L is from the pivot to point B, so straight to the right, and T is at that angle, so between those two, it's just the angle theta, or 180 minus the angle theta, either way. Sine of theta and sine of 180 minus theta would be the same thing. So this gives us what? LT sine theta minus XW equals 0. So add XW to both sides and divide by L sine theta. So XW equals LT sine theta. Divide by L sine theta, and we get T equals XW over L sine theta, or a nicer way to write it would be W over L sine theta all times X. So the tension as a function of X is just a bunch of constants times X. It's going to be linear in X. Okay, that was part A. Part B said, find the horizontal and vertical components of the force exerted on the bar by the pin at point A. Okay, so I guess they want us to just express it in terms of the stuff that they already gave us, because it's not like we have actual numbers to solve for here. So let's see what we can do. So since I already have T over here expressed in terms of all the other stuff, I can go ahead and solve for Fx up here and Fy down here. So for Fx, it's equal to T cosine theta. So Fx equals W over L sine theta times x, and then all that times cosine theta. Okay, cosine theta over sine theta. Well, sine theta over cosine theta is equal to tangent theta, so cosine theta over sine theta is equal to 1 over tangent theta, or cotangent theta for those of you who want to be fancy. But W over L tan of theta times x, that would be fx. And then Fy is going to be, let's see, t sine theta plus Fy minus W. So add a W, subtract t sine theta. Fy is going to be, Fy is going to be, I probably don't even have the space for it here, but we'll try. Fy is going to be W minus t sine theta, that's W minus W over L sine theta x times sine theta. Sine theta and sine theta cancel out, so you get W minus W over Lx. Factor out the W, and you get, I guess I'll continue it down here, Fy equals W minus W, and then I'll put the x and L together like this. Factor out the W. And yeah, I think that's the nicest I can make it look. I mean, you probably could have stopped right over here without having to factor out the W, but you know, in case you want to take it as far as you can, that's probably where I would stop. I don't see anything further you could do with it there. And now for part C, it says with, so this was part B, and then for part C, it says with W equals 315 newtons, L equals 2.76 meters, theta equals 32 degrees. Find the maximum distance x before the wire breaks if the wire can withstand a maximum tension of 520 newtons. Well, let's assume the wire is already near the breaking point. Let's assume that T is already 520 newtons. T max is 520 newtons. Let's set T equal to its max and see what x would be there. So I can just reuse what? I can reuse the result from part A and solve for x. So T max of x, 520, equals W over L sine theta x. W, 315, over L sine theta, so that's 2.76 sine of 32 times x. Okay, and then the rest is just algebra. We know how to do all that, but since it's quick enough, I'll do it. 520 times 2.76 sine 32 divided by 315 is 2.4144. I'll just round it to 2.41. So x equals 2.41 meters. Does that check out? Is that less than the full length of the bar? Yes, the bar is 2.76 meters, so 2.41 meters it is possible. If x was greater than 2.76, then that would just mean that there's no distance, there's no place you could put that weight and have the rope ever be at risk of snapping. Or what was it? A wire, not rope. Details, details. I would like to do a problem where, so let's see, what have we done? We've done problems where there is no net force X. So let's see. Yeah, we've done problems where there is no net force X. We just did a problem where there is a net force X, and also at the same time a problem where a clever choice of pivot allows you to eliminate two unknowns all at once. And it was also an expression problem, so that was all nice. We've done examples of problems where there is a force of gravity on the supporting beam or whatever supporting structure you have in the problem. And we just did an example where the force of gravity is negligible on the supporting structure, so we've got that covered. I would like to still do a problem where the actual length of the support is not given, which we kind of did do here, but this isn't quite what I'm looking for. It'll make more sense once I find one that I can use. Let me see. Do we have any good ones in here? I mean, I can make one up. I think that's what I'm going to have to do. So let me take this problem, which mentions a ladder, and see if I can make some edits to it. Give me a minute to think about how I want to do this. Okay, let's see if this works. So let's say we have a ladder propped up against a wall, because we still need to do a ladder problem anyway. So let's say we have a ladder propped up against a wall. And it is at an angle of theta. It is at an angle of theta when it is just on the verge of slipping. When it is just on the verge of slipping. So on the verge of slipping. It hasn't slipped yet, but it's on the verge of slipping. has a mass ladder is going to be M, capital M, and then we're going to have a person on the ladder, and the mass of the person on the ladder is going to be, let's say they have a mass of 2m. They weigh twice as much as the ladder. Actually, I guess depending on the type of ladder, 2m might not be enough, because some ladders are a lot lighter than the people they're supposed to support. But if it's not a person, let's assume, I don't know, if it's not realistic for a person, we could say that it's a block or some object on the ladder. And let's say that the person is standing, we'll say that the ladder has a length of L, and we will say that the person is standing at We'll say that the person is standing at 2/3 L up the ladder when the ladder is on the verge of slipping. So I want to do what now? I want to find an expression. I hope this is actually doable, but I'll modify it as I go if I haven't given enough information. Find the coefficient of static friction necessary to prevent slipping in terms of M, L, theta, and physical constants as needed. By physical constants as needed, that probably just means little g for gravity. As needed. I can spell today. Totally. That is a very ugly looking N. Okay, let's see what we can do with this. So we would have, if I were to try and complete the diagram, what forces do we have here? We have, since it's propped up against the wall, and let's say that there is no friction against the wall. That's another thing I probably should have specified. No friction against the wall, but the wall does experience a push from the ladder, so it's going to push away. So the wall is going to exert some normal force. I'm going to call it normal force wall. And there's going to be a normal force from the ground, so I'll draw that force as well. Normal force ground. Normal force, or I'll call it normal force floor. That's a little bit shorter to spell. And then what else? We've got the weight of the ladder itself is going to be acting at the center of the ladder. So that's going to be what? Big M times G. The weight of the person is going to be 2 big M times G. Acting over here. And I can already see I'm not going to have enough space to write some of the stuff that I wanted to add on to this. I'll probably have to redraw the diagram or something. And I think, is that all of them? No, there's one more force, which of course is the friction force, the static friction force that is preventing this ladder from slipping. And what direction must that static friction force be? It has to be to the right, because that's the only way that your net force X can be 0. Since you've got normal force from the wall to the left, you need your static friction force to be to the right. So that's force, friction, static, has to be to the right. But also the other thing is, if the ladder is going to slip, which way is it going to slip? Well, it's going to slip with its top is going to go down, which means its bottom is going to go left. So static friction is going to oppose that attempted leftward motion. Direction of static friction is opposite to the direction of attempted relative motion. The relativity part is less important here, since we're talking about just a wall and a ground that don't move. At least from our usual perspective, they don't move. I think we do have enough information to be able to do this. Yeah, because net force Y has to be 0. Well, there's 3 forces. So let's see, net force X has to be 0. Net force Y has to be 0. And net torque has to be 0 about any pivot. Net force X being 0 means normal force floor, the only upward force I have, minus mg and minus 2mg has to be 0, which means normal force floor is equal to 3 mg. And then wait, did I do that? I did that for X. Okay, I'll fix that. There, now that's net force Y, and this will be net force X. So net force X, I'm going to do force to the right, force friction static, minus force to the left, normal force wall, has to be 0. That tells me that normal force exerted by the wall equals force friction static equals, well, if it's on the verge of slipping, then it's not just greater than or equal to, it's just straight up equal to mu static times normal force floor is equal to mu static times 3 mg. Okay, so far so good. Everything can be expressed in terms of big M and G, and constants like 2 and 3. Okay, net torque has to be 0 about any pivot, so wait a minute. Can't I just solve for mu static from? No, wait. No, I can't yet. Okay, let's write our net torque equation and see what comes of it. So I have some options here. I will do, where do I want to place a pivot? I think the better place to put our pivot will be down over here at the bottom of the ladder, because then I can eliminate two forces. Or rather, two torques from those forces, not the forces themselves. And let's use counterclockwise as our positive direction. So net torque is going to be 0 equals, well, we're going to have 0 from normal force floor and 0 from the force of static friction. So 0 and 0 there. And then as I move along the ladder, the first force I encounter is the weight of the ladder itself, which is going to cause a clockwise torque if we're pivoting at the bottom of the ladder. So that's going to be minus. And then the distance is, well, we don't know L, but we can just express it in terms of proportions of L. It has to be halfway up the length of the ladder, because that's where the center of gravity of the ladder would be. So that's going to be 1/2 L, distance away from the pivot, direct distance, that is, displacement to be more specific, times the force is mg, times sine of the angle, times sine of, this is something we have to be careful about here. So this angle theta is not the angle to use. So I'm going to redraw this part. So we have this angle as theta, and then we know that our pivotal displacement is in that direction, and we know that our force is in this direction. So what we want is either this angle or this one. Either of those will do. I'll just use this smaller one over here. And if I complete this line over here, I can make a right triangle, and we can see that this angle is 90 minus theta. So we can do sine of this angle, sine of 90 minus theta, or sine of 90 minus theta, that can also be expressed as cosine of theta. That can also be expressed as cosine of theta. Wow, it's almost 3 hours already. And here I thought I was going to have plenty of time to cover moment of inertia and center of mass. Okay, that's probably going to be pushed back to later. I'll talk about moment of inertia conceptually at the very least at the end, because I do have a mini video to play covering that idea, and we'll dig into it more deeply in the next stream, which will hopefully be tomorrow. But wow, how the time flew. Anyway, as sine of 90 minus theta, I can rewrite that as cosine theta, which I'll do the second time I copy this over. Next up, we've got torque due to the weight of the person, so that's going to be, they're 2/3 L up the ladder, and they're going to cause a clockwise torque. So that's going to be minus 2/3 L times 2 mg times same angle, sine of 90 minus theta, which is equivalent to just cosine of theta. And next up is the normal force from the wall. So that is going to cause a counterclockwise torque. So plus normal force wall, which we said is equal to mu static times 3 mg. It's going to be a pivotal displacement L away from our pivot. So L times normal force wall, which was equal to 3 mu mg, 3 mu static mg, times sine of, let's see, so pivotal displacement is that way, normal force wall is that way, we need to find that angle. Well, if I were to draw the ladder again, if this angle is theta, and we're trying to find this angle, because we'd be doing between that direction and the direction of the normal force, we're trying to find this angle, well, that's just going to be theta, because if these two lines are parallel, you already know, you've seen this Z shape a number of times if you've been following this course from the beginning. When you've got two parallel lines and then you've got another diagonal crossing both of them, then these, what are they called, opposite interior angles have to be equal to each other. So yeah, that's just going to be sine of theta. Okay, this we can actually solve for mu static. So one thing you'll notice here is that the length itself actually gets canceled out. Everything has length in it, so if I divide the whole equation by L, 0 divided by L is still 0, and then I can just get rid of all the L's. It's similar to what happens in mechanical energy conservation problems where everything has mass in it that gets canceled out. If you're familiar with that, then this shouldn't look too foreign to you. All these L's cancel out. Let's see. I want to keep this on the right hand side. I want to move these over to the left and rewrite the sine 90 minus theta as cosine theta. And I can factor out, come to think, well, I'll do that in a minute. So 1/2 mg cosine theta plus, that's going to be 2/3 2mg, so 4/3 mg cosine theta equals 3 mu static mg sine theta. Okay, 1/2 mg plus 4/3 mg cosine theta would be what? 1/2 plus 4/3. 1/2 is 3/6, and 4/3 is 8/6. So 3 plus 8, that's 11/6. So that's 11/6 mg cosine theta equals 3 mu static mg sine theta. The mg's cancel out. Come to think of it, I could have canceled them out with the L's all the way back here if I had been thinking far enough ahead. And if I divide by 3 and divide by sine theta, 11/6. Dividing by 3 means multiplying 3 in the denominator, so that becomes 11/18 cosine theta over sine theta. Cosine theta over sine theta equals mu static cosine theta over sine theta, like earlier, is equal to 1/tan theta, or cotangent theta, again, if you prefer, but usually you're not expected to know about cotangents, cosecants, and secants for AP Physics. Well, at least not for AP Physics 1. For Physics C, I've never actually seen it on the AP exam, I don't think. But if it's a calculus-based physics course, then they expect you to at least know the stuff you would learn in pre-calculus. So secant, cosecant, and cotangent, I would argue, is fair game for Physics C. Although I don't think I've ever seen them actually have to use it anywhere. I mean, it did pop up in that one equation that we did in projectile motion. It did pop up in that one projectile motion problem that we did with the basketball player, I believe. But that was just an option. We had the option of writing, what was it? There was a secant squared in the equation that we also just could have written as 1 over cosine squared. Anyway, cosine over sine, I'm just going to write it as 1 over tan, so it's going to be 11 over 18 tan of theta equals mu static. So 11 over 18 tan of theta equals mu static. Circle the whole thing. I don't know why I just circled the mu static there. Brain malfunction. It's been too long of a day. Now let's try this for, let's say for theta equals, well, hold on. Let me make some predictions here. So a ladder would be more likely to tip over the shallower the angle is. Because the shallower the angle, the lower the normal force. Wait, does that actually make sense? Here, the normal force would actually have to be the same, regardless of the angle. But at the shallower angle, the torque due to the weight of the ladder itself and the person on the ladder would increase because the angle they make with the pivotal displacement gets closer and closer to 90 degrees, gets closer and closer to maxing out. So yeah, the shallower the angle, the more likely the ladder is to tip over, which is something we experience in real life as well, right? You probably want the ladder to be kind of closer to upright than flat in order to avoid tipping over. So yeah, that makes sense to me. So dividing by tan of theta. So the shallower the angle, the smaller tan theta is, which makes a smaller denominator here, which requires a higher static friction coefficient. Okay, yeah, that makes sense to me. It requires a higher static friction coefficient at shallower angles. Okay, so let's try it for something like, I don't know, 60 degrees. So 11 over 18 tan of 60 degrees. At 60 degrees, you only need a coefficient of friction of 0.35, which does require some rough material, but still pretty reasonable. What about a shallower angle, like 20 degrees? 11 over 18 times 20. Oh, now you need a coefficient of static friction of 1.679, which, yeah, good luck finding a material that's rough enough to hold that ladder still. Okay, yeah, that's consistent with what we know from life experience. Okay, that was actually not as much of a disaster as I thought it would be. Find mu static in terms of m, L, theta, and physical constants as needed. All we needed was theta. All we needed was the theta. But hey, they're going to write the problem like this just so that they make sure students are actually being careful and not just... Because if the problem was written and they told you to find it just in terms of theta right from the get-go, then some students might get trigger happy and just ignore the M's and the L's. But what's more likely to happen is some people will look at it, think it's impossible, and just give up on the problem and not even try. I think that's it for torque examples because we're already past the 3-hour mark. So let's talk about center of mass and moment of inertia. I want to talk about moment of inertia first. We'll talk about it just kind of quickly as a concept, and then we'll dig into it more next time. But today we mainly dealt with situations where the net torque was 0 and the object was not rotating. Well, next time we're going to dig deeper into what happens when the net torque is not 0. So there is an equation which some people call the Newton's rotational second law. Not really an official name, but you'll see why it's named that. It says net torque equals something new that we haven't seen yet, called moment of inertia, times angular acceleration. This is basically the rotational version of Newton's second law. This is net force equals ma, except you replace force with torque, which is some sort of rotational force. You can think about it. The more torque you have, the more you can rotationally accelerate an object. A is just the regular translational acceleration of an object, and mass is just a measure of an object's inertia. So there's also this thing that we replace the mass with. It's kind of like rotational mass. It's called moment of inertia. I is called moment of inertia. If an object's inertia is its resistance to being accelerated, then an object's moment of inertia is its resistance to being rotationally accelerated. An object's resistance to being rotationally accelerated. Some things rotate really easily. If I put this pen over here and let it go, it tips over rather quickly. If I try to balance it on the palm of my hand, very, very difficult to get it to work. I might have better luck with my calculator, just slightly better luck, but it does tip over if I don't catch it. But it is a little bit more difficult than the pen. It does take a little bit longer. It's barely noticeable, but if you pay attention, you might be able to feel it if you can't see it. And let's see, how about this ruler over here? I don't even think, yeah, it's too long to fully go under the camera, but let me see if I can at least get some of it under the camera. And okay, yeah, I had a little bit of a better time balancing it on my hand, but still, it tips over pretty quickly. So fortunately, I pre-recorded a demonstration that illustrates the balancing act a little bit better But before that, let me go ahead and write down the equation for an object's moment of inertia, assuming that it is a point mass. So, as you might guess, the more mass an object has, the more resistance it has to being rotationally accelerated. That makes sense. The more stuff there is packed into an object, the more matter that is in there, the more stuff that needs to be accelerated, and therefore the more effort, the more torque that's needed to cause all of that stuff to rotate. That makes sense, and that is something we find in the moment of inertia for a point mass. Moment of inertia for a point mass. What is a point mass? A point mass is an object that's treated as if all of its mass exists at one point. So basically we're going to be dealing with two different kinds of things here. We're going to be dealing with point masses, just mass that's concentrated at a point. We'll treat tiny things like atoms, or we don't even have to go to the atomic scale. We could treat regular everyday objects like billiard balls and, I don't know, blocks and cups and stuff as point masses, depending on, what scale we're working on. If we're talking about, for example, even the Earth or the Moon, if we're talking about the Moon relative to the Earth or the Earth relative to the Sun, we could treat the Moon or the Earth as being point masses when you're talking about that big of a scale. So it's really just a matter of perspective. The Earth and Moon could be considered really, really, really tiny points in space when compared to the Sun, or at least when compared to the distance between the Earth and the Sun. So when objects are really, really small, relatively speaking, that's when we often treat them as point masses. We treat them as if all of their mass is concentrated at one point. The other type of object that we will deal with is just some rigid object with its mass distributed in some way. So things we will encounter will be things like a rotating cylinder or disk. And for that, we're going to be specifically talking about its moment of inertia for an axis of rotation that goes through its center. So it'll be rotating, let's say this way, revolving around that axis. And here, some of the mass is going to be really close to this axis of rotation. Some of it is going to be farther out. The farthest mass is going to be at a distance of, well, whatever the radius of this cylinder is. And if we treated this whole thing like a point mass, we wouldn't be telling the entire truth behind how this thing rotates. But if we were rotating it, let's say, instead of it rotating around an axis that goes through the object, if we took the whole cylinder and we were rotating it around, I don't know, some external axis, if it was going in, let's say, uniform circular motion of radius, what do I want to call this? I guess we'll call it L, since big R is already taken, where L is significantly larger than big R, then yeah, in that case, around that rotation axis, we would treat this cylinder like a point mass again. Just like what I said earlier about how we can treat Earth or the Moon as point masses when we're talking about something as large in scale as our solar system. So it really just depends on scale for the most part. And again, we'll dig into this in more detail next time. But for now, what I want to give you, I'll just introduce this equation and give some intuition behind it. We have the moment of inertia for a point mass is going to be all of the mass at that point times the square of the distance between that point and the axis around which it is rotating. So what this means is objects don't just have one moment of inertia, they have literally infinite moments of inertia, one for each possible axis of rotation you could come up with for them. If I take this cylinder, so I had an axis of rotation through its center, I had an axis of rotation outside. Over here, I could have other axes outside of the cylinder at various distances. I could have other axes of rotation inside the cylinder itself, but not going straight through its center, and that would cause some different rotation. Forget about cylinders, take something like a rod. I'll just use a ruler as an example. The difficulty with which you can swing it back and forth will depend on where you grab it from. If I'm trying to rotate it around this axis, I have a lot more difficulty than if I'm trying to twirl it around here. Notice how much more easily it twirls around here. If I try to twirl it around here, I can still do it, but it's a little bit more difficult than it was at the center. Fun fact, the easiest axis through which you can rotate something is through its center of mass. That's why the middle of this ruler will be the easiest to rotate it. We can go over the math at a later time. I'll have to figure out where I want to fit it in, but yeah, the middle, the center of mass, is where you get the least resistance, and anywhere farther away, it just gets harder and harder to rotate it with the same amount of force, or rather with the same amount of torque. So yes, mass is a factor, but distance, where your axis of rotation is, that's an even bigger factor. That is an even bigger factor. And I'm going to demonstrate this with, so we already demonstrated what happens if you move the axis of rotation on the same object. Mass is the same, but you're changing the axis of rotation. You're changing the distance between the mass and the axis of rotation. Here, the farthest parts of this ruler's mass are, 6 inches away, plus the little extra that are at the ends of the ruler for whatever reason. So when the axis is just through the center, and you're twirling it through the center, the farthest parts are just 6 inches away. But if I move it, say, to, I guess this would be the 9-inch mark, now the farthest part is 9 inches away. And sure, I made this part closer because this part is now 3 inches away, but the increase in moment of inertia for this side by moving from the 6-inch mark to the 9-inch mark, the increase in moment of inertia that I created on this side of the ruler will always outweigh the decrease in moment of inertia that happened for this other side of the ruler. We can look at the math later to convince ourselves that this is true, but for the sake of time, I will leave that out for today. So we've done this. We've done moving the axis of rotation to increase or decrease moment of inertia while maintaining a constant mass. There's another thing I can do, which I guess is kind of the same thing, where I rearrange the mass. So for that, I have this video that I prepared. Let me go ahead and turn it on and see if it will play. I think I need to hit this first. And then, do I just hit this? No. Hold on, I need to... What you see here is an extended umbrella. Notice that I don't have much difficulty keeping it balanced. It doesn't tend to tip over very well. It doesn't gain a lot of rotational acceleration from gravity. that means it has a very high moment of inertia when extended. However, if I were to compress it, now it tips over a lot more easily. I'm not faking it. You can try this experiment yourself if you have this type of umbrella, and you can see, or to put it more precisely, feel how much more easily it tips over when it's, for lack of a better term, compressed. All right, and that is done. So that is my classic umbrella demonstration, which I do for students every year. So if you have one of those umbrellas, definitely do the experiment, as I said in that mini video over there. Safely, don't poke anybody's eye out. Again, I will bring out the clips and show the receipts if anybody's parents try to sue me for any shenanigans that you guys end up pulling off. But yeah, just rearranging the mass and increasing its distance from your axis of rotation. In that demonstration, the axis of rotation would have been where the umbrella's handle met the palm of my hand. That increases the resistance to rotation. That increases the amount of torque needed to achieve the same angular acceleration that you would get from letting a pen tip over in your hand. And why is that? Let's give some intuition as to why increased distance could possibly cause an increase in demand for torque. So let's say I have a pivot over here representing, I guess, something that I'm trying to balance in the palm of my hand. And let's draw just a stick, some long generic object, a meter stick, for example, will do the trick. Why is it that the farther away the mass gets, the more torque it takes to get it to rotate? Well, if you chop this thing up into pieces, if I were to just cut this into little pieces, then what you'll notice is that this bottom piece over here only needs to go this far. And let's say this tips over in 2 seconds. Probably shorter than that, but let's say 2 seconds. And then this part needs to also move this far in the same 2 seconds. Oh, and then the top parts need to move this far. All in the span of 2 seconds? Good luck with that. So, because the farther parts of the object have a longer path to cover, and it's not like they can just lag behind. It's not like the lower parts can tip over first and then the bottom parts come after it. If that was the case, then what you would see, is you would see the object, best case scenario, you would see the object bending, where its closer parts will have already fallen over, while its farther away parts are still catching up. You would see something like this. The closer parts would have already come down, while the farther away parts have only gotten this far because, well, yeah, they haven't had enough time to trace out the full arc of where they need to travel. So best case scenario, you would see your object bend, and I suppose you could see that if you try using this ruler, if you just keep on safely, not in the presence of other people or glass or other objects that are breakable. If you would just stand up and kind of whip with the ruler, you can see if you try to forcefully swing it down 90 degrees like you're practicing with a kendo sword or something. You could see that happening, especially if you put a camera up and record it and then replay it in slow motion. You could see that happening. But if it's not something bendy and you really, really forcefully try to move it as fast as you can, I don't think it's humanly possible. You would probably need a really strong machine in order to do it. But what would actually happen, worst case scenario, is the bottom part moves so much faster than the top part that the top and bottom separate from each other so that the bottom can get to its destination while leaving the rest behind. In other words, the object would break. The object would break and the top of the object would just break off of it. But usually what happens is, because the farther away parts can't move fast enough, the whole thing is slowed down. Either that, or of course you put in more force and by extension more torque, which allows even the top parts to move fast enough to tip over at whatever speed it is. And it's not just for tipping over, of course, it's for any and all rotation that you're trying to achieve, but tipping over is the easiest one to explain, at least in my experience, because you don't have to set up any sort of elaborate equipment. You don't have to set up any machinery, really. You can just let gravity do the work for you when tipping things over. Let me see. Was there anything else I wanted to comment on before leaving the rest of this topic to next stream? Not really. So next stream we will talk a little bit more about this. Well, actually probably a lot more about this. We'll talk about how to get moment of inertia for a system of multiple objects, and we will talk about special moment of inertia formulas for special mass distributions like the cylinder and the solid sphere and the hollow sphere and stuff like that. And we will also see how moment of inertia basically replaces mass in a lot of our previous equations in order to give us the rotational versions of them. So again, as I mentioned last time, if you've been memorizing your equations from previous chapters, a lot of the new equations we're going to see are just literally any equation we had before that had mass in it, replace it with moment of inertia. Anything that had acceleration in it, replace with angular acceleration. Anything that had velocity, replace with angular velocity. Anything that had force in it, replace with torque, and so on and so forth. If you just make those replacements, replace your variables with their rotational analogs, you will probably get the rotational version of that old equation, and it will probably work exactly as you might expect. So that is all I have for most of you. Physics 1 students, you are dismissed. Physics C students, let's talk about one last topic, which is calculating the position of an object's center of mass. Oh, and I guess for the Physics 1 students, if you haven't left yet, for homework, I would just look in the course plan and look at some of the book problems from the OpenStax textbook, or if you have your own textbook, look at some of the equilibrium torque problems in there. Oh, actually, let me give you this problem before I send you off. Some of you probably already clicked away. But that's okay. Let me give you this problem, because this problem stumped me a few years ago until I had enough time to think about it and realize what I was doing wrong. So you have an object. You have this plank that is supported by 2 pegs. And let's say these 2 pegs are, I'll just make up a number. Let's say these pegs are 1.75 meters apart. And let's say that this board is let's say that the board is 3.75 meters long, and these pegs are not fastened to the board. The board is literally, you can pick it up and it was picked up and placed on top of these pegs. And so you have a person who starts off by standing halfway between the pegs, and they start walking. And the question is going to be, let me think here for a second. Is this even, hold on. I think I might want to actually make this, no, 3.75 will work, but yeah, let's actually make this 4 meters. Yeah, let's make this 4 meters. So the question would be, what will the force be in this peg just as this plank of wood is about to tip over as this person continues to walk? How far will they be able to get, first off, and then what is going to be the force in each of the pegs when the board is about to tip over? And I guess I need to give you, let's say, the mass of the person is, let's make them 65 kilograms. And the mass of the plank, let's make that 20 kilograms. So yeah, that is my question. So how far before the plank tips over, and what is the force exerted on the plank by each of the pegs when it's on the verge of tipping over? Those are the 2 questions. So I guess this will be force left and force right. And those are also my questions. What will they be once this plank is about to tip over? Okay, that'll be your homework for Physics 1. Now, for the Physics C students, let's talk about finding center of mass, how to calculate its position, and the differences between center of mass and center of gravity. So, to find the center of mass, we'll start with just some point masses, and then we'll talk about some continuous objects with uniform density. So if I have a collection of point masses and I just create a coordinate system and lay them onto that coordinate system, and the coordinate system you choose doesn't actually matter, whatever result you get will be correct according to your coordinate system of choice, and I think I will demonstrate that in a minute. So let's say I have a couple of objects over here, and they're going to have different masses. Let's say this one is 3 kilograms. Let's say that one is 2 kilograms. And let's say this one is 5 kilograms. And let's say that these two masses are 8 meters apart. And then this over here is, I'm going to go ahead and call that 4 meters away. And I want to calculate the position of the center of mass of this system. So center of mass by definition is the average position of the mass of a collection of point masses. If we're talking about an object, a single solid object, then you can think of chopping it up into little pieces and calculating how much each piece contributes to this weighted average position of the entire mass of the object. Or in this case, I'm just looking at the simple case of 3 point masses and trying to find the weighted average position of their mass. Trying to find a point where I can treat it as if these objects were tied together, let's say they were bound together by magic rods, invisible magic rods that have no mass, then what's the part of the object that could be treated as the center of the system? If I were to hurl this collection of 3 particles, which are again magically connected by rods, let's say, what would be the point where if I tracked that point, I would notice that that point moves exactly the way that a single object of mass 2 plus 3 plus 5, a single 10 kilogram object would behave? What is the 10 kilogram object that I could replace this 3-piece object with to get basically the same result from throwing that new 10 kilogram object with the same force at the same angle in the same direction? How could I get the same, I guess, if I were just to throw an object, how would I get the same path for that projectile? Let's say I just threw it at an angle and it engaged in projectile motion. If I throw this triangle of points in the air, it will, it'll twist and twirl. Let me just draw a triangle instead of drawing the points on the triangle. So maybe it'll look like this at one instant, and then sometime later, because it's also twirling in the air, the triangle is rotating as it goes. And then maybe it's completely upside down over here, and then maybe it's tipped over like this at this point. And there's some sort of point that remains on this arc if you keep track of it. So my question is, where would that point be located if that point moves as if it were just a regular 10 kilogram object? That just moves like this, like what we're used to. That's what we're trying to find. So because it's a weighted average, all we have to do is just calculate it like a weighted average. We did this way back in the beginning of the course with trying to find average speed. We said it was a weighted average, and it was weighted by time. You couldn't just add up all the speeds and average them. You had to multiply each speed by how much it actually contributes to the average. And the way that we measured the contribution to the average there was by time. The more time you spend at a certain speed, the more it contributes to the average. If I traveled at 60 miles an hour for 59 minutes and then 1 mile per hour for 1 minute, then it wouldn't be fair to say that my average is 60 plus 1 divided by 2. I spent way more time traveling at 60 than I did at 1. So it would make more sense that my average is a lot closer to 60. It would make more sense that my average speed for that trip would be 59.9 something. Well, over here, mass is going to be weighted by its position. Over here, mass is going to be weighted by its position. So let's forget about this 3-object collection of masses for a minute, and let's just do 2 objects. Let's say that I have 2 objects. Let's say I have a 10 kilogram object here and a 20 kilogram object here. And I'm trying to find their mutual center of mass. Well, it's got to be a lot closer to the 20 than it is to the 10. In fact, twice as close to the 20 as it is to the 10, because the 20 is twice as much mass. If there's twice as much mass on the right than there is on the left, then it has to be 2 times as close to the right than it is to the left. So I would actually need to split this into... I would actually need to split this distance into 3 pieces, and I would just put my center of mass would have to be here, because it would be whatever this distance is, 1 distance away from 20, twice as close, and 2 distances away from 10, twice as far. Hopefully that made some semblance of sense, but another way you can look at it, let's say that this full distance between them is d, and this is 1/3 d, and this is 2/3 d. Basically, what I'm trying to look for is some point where the distance of the 10 kilograms to that point, so 10 kilograms times the distance plus 20 kilograms times the remaining distance, 20 kilograms times the remaining distance, which, since I've already solved it, isn't really that much of a surprise, is equal to wait a minute, what would it be equal to? Am I doing this right? Hold on, 10. Yeah, divided by the total mass, so divided by 10 plus 20 would have to be equal to whatever this position is. Hold on, let me actually multiply this out and see what I get. So 20 over 3 plus 20 over 3 is 40 over 3 divided by 30. Wait, 40 over 3 divided by 30 all times d. I don't think this even makes sense. 40 over 94. Okay, I think I'm just having a brain malfunction. What I wrote here doesn't even make any sense. Okay, forget what I was saying there. It's probably because I'm trying to explain it in a rush, since we're almost at 4 hours now. Oh my. It's a good thing I canceled yesterday because I did not have 4 hours yesterday. I kind of had a feeling that I wouldn't be able to make it in time. And now that's confirmed. Okay, let me slow down and try to do this again. So we are looking for, so it's going to be 2/3 D and 1/3 D, but the way we want to do it is we're looking for a position such that we are looking for a position that is a distance, let's call it a distance x away from the 10 kilogram object, such that 10 times x is equal to 20 times d minus x. Yeah, that's what we're doing. We're looking for a position such that 10 times x is equal to 20 times d minus x. And if we solve that, we should get x is equal to 2/3 d. So 10x equals 20d minus 20x. Add 20x to both sides. 30x equals 20d. And then divide by 30, and there you go. X equals 2/3 d. Okay, there we go. That wasn't too bad. So yeah, we're looking for a point such that if you multiply each mass in the system by its distance from that point, you get the same amount. You get this same quantity. So let's go ahead and actually try to solve for that here. So I'm looking for a position where I want to solve this both in the x and in the y separately. I want to do it separately for the x and the y. So what we're going to do is we're going to take each mass, we're going to multiply that mass by its x or y position according to this coordinate system, and we're going to add all those, add each mass times its position, and then we're going to divide that by the total mass. And then we're going to divide that by the total mass, because that is basically what we did over here. That's basically what we did over here. We did, let's see, if I rearrange this, we had 10x, so I had 10x plus, what did I do? Essentially, what I did over here is I did 10 times x plus 20 d minus x divided by 30 equals, well, would have to be equal to x, right? I think I'm just confusing myself with this. I'll play around with this later. It's too late at night for me. Let's just continue on with this and go over the formula at the very least. So for the center of mass, x coordinate and y coordinate, for the x coordinate, we're going to say x bar, or if you prefer, xcm for center of mass, and more recently I've also seen com, which I don't really like because that can be confusing. I've seen, because I saw in a textbook a couple weeks ago something where the O was capitalized, and I don't like capitalizing the O from of in an abbreviation. I thought maybe the COM stood for something else. I'm not sure, because you could easily think there was a word like, I don't know, compression, compressor, or something like that. When you see X subscript com, you could think that it's standing for compression distance, for example. So yeah, I don't like that. cm for center of mass is what I prefer. But yeah, you basically just take each mass and multiply it by its distance from some position. I'm just going to say distance from this vertical axis that I've drawn, and divide by the total mass. So basically the same thing that we did when calculating average speed. You took each speed, you multiplied by the time you were moving at that speed, and then you divided by the total time. Same thing here, each mass divided by its distance divided by the total mass. So 3 kilograms times 0 plus 2 kilograms times, we're specifically just looking at the x's, not the y's. So the 2 kilograms is at 8 meters. And then plus, can I even squeeze it in here? Plus 5 kilograms times horizontally, it's at 8 meters from this axis. So it'll be 5 times 8. And then we need to divide that by the total mass. So 3 plus 2 plus 5, divide that by 10. I probably should have written 3 plus 2 plus 5 out. I'll do that for when we do the y. Okay, so that's going to be 0 plus 16 plus 40, so that's 56 over 10, that's 5.6. That's 5.6, so wherever our center of mass is, it's, let's see, that would be 4, that would be 6, so, and that would be 5, so 5.6 is somewhere over here. Actually, the place I drew my dot is, it might actually be spot on, but somewhere along here is going to be the center of mass of this system. And then now I want to do the same thing for the y. So y bar, or y center of mass, whatever you want to call it, is going to be 0 times 3, 0 times the 3 kilograms, plus 0 times the 2 kilograms, plus 4 times the 5 kilograms. We're at a y of 4 for the 5 kilograms. And then divide that by 3 plus 2 plus 5. Positions that are closer to more of the mass will contribute more to the average y position. So we should be a lot closer in terms of y and in terms of x to the 5 kilograms than we are to the 3 or the 2. Actually, to be fair, since we have 5 kilograms down here and 5 up here, I think we might actually just be at exactly 2 meters, right? Yeah. Because if you think about it, if I were to, let's see, so there's 4 meters. If I were to draw that dividing line over there, then I see that I've got 5 kilograms above this line and 5 kilograms below this line. So since there's an equal amount of kilograms above and below, the line should be just right in the middle for y bar. So yeah, that makes sense. 4 times 5 is 20 over 10 equals 2. So yeah, actually my guess wasn't too far off. It was just a little bit too low. The center of mass of this system is right over here at this point. Now, I said that it doesn't matter what coordinate system you use, and that your center of mass will just be at the same point according to that coordinate system. Well, that's actually going to be true, because what if I just shift my coordinate system down by 1 meter? What if I shift the coordinate system down by 1 meter? So what if I do this? I keep everything else the same, but I move the 3 kilograms up to 1 meter and the 2 kilograms also up to 1 meter, and the 5 kilograms up to 5 meters. So make this 5 meters and make this 1 meter. I could have also shifted it in X, but we don't need to do that. So what does this do? Well, this just adds 1 to all of the Y's. So if I go back to this equation, basically I just get an extra 1 times 3 plus an extra 1 times 2, plus I already had 4 times 5 before. Now I'm going to get 5 times 5, because the 5 kilograms is 5 meters away in terms of Y. So I've basically just added 1 of each. I added a 3, I added a 2, and I added 1 5 to this total. So I'm going to do the original 4 times 5 plus 1 times 5. I just added a 3 and a 2 and a 5. And I'm dividing by 3 plus 2 plus 5. So I just added 1 to the total. So now instead of 20 over 10, I'm getting 30 over 10 equals 3. And yeah, my Y is going to be at 3 meters according to this coordinate system. My Y center of mass is going to be at 3 meters according to this coordinate system, but that's still, relative to the objects, that's still 2 meters away from the 5 kilograms and 2 meters away vertically from the 2 and the 3 kilograms. This is still 2 meters. The center of mass is going to be at the same place relative to the object regardless of your coordinate system. So any coordinate system you choose will be fine, kind of like what we did earlier today with being clever about your choice of pivots for torque. Be clever about your choice of coordinate system. Try to get a bunch of zeros. Try to get a bunch of your masses on the axes and get one of them on the origin, so that you don't have to spend as much time calculating stuff. If the coordinate system isn't going to matter anyway, you might as well take advantage of that. And that is how you calculate center of mass for a collection of point masses. You do it separately for the X and for the Y, and if you had a 3-dimensional case, which they probably won't give you, then you would also do a calculation for the Z, and that's it. The more mass there is at a position, the more that position is represented in the average. So each position just gets multiplied by the amount of mass at that position. And then you divide by the total mass and you get your weighted average that way. That's all it is when you're dealing with point masses. If you're dealing with continuous mass distributions, well, apart from the situations that require calculus, which we will reserve for later, let's take a look at something like a piece of wire that is bent into some weird shape. Let's take a look at a piece of wire that's bent into some sort of shape. So let's say my piece of wire looks like this, and then it's just bent in this sort of way. I don't know, somebody took like a clothing hanger and decided to turn it into some weird shape. That's probably too many pieces, but that's okay. Let's say that this thing has... Actually, I don't even need to know its total mass. All I need to know is that this object's mass is uniform. I just need to know that its mass is uniformly distributed. Uniformly distributed mass. And I guess I need to know not even the length necessarily, but just the relative lengths. I don't even need actual numbers, but let's go ahead and assign some numbers to this. So I want this piece to be, we'll say that that is a length of 3. And then that means this over here is a length of 2. And this over here will be a length of, I'll call that 2.5. I'll call that 1.5. I will call that 3. We'll say this is we'll say that's 4. And we'll say this is another 1.5. Maybe I put too many twists in this thing. And we'll say that's another 3. In whatever units you like, centimeters, meters, it doesn't really matter, because as long as you're consistent with your units, the distance units are supposed to, well, the distance units don't cancel out. The distance units that you put in are the distance units that you get out, but the mass units are going to cancel out, because you're going to have distance times mass plus distance times mass and so on and so forth, all divided by mass. So if all of your masses are in grams, for example, you'll have gram meters at the top divided by grams, leaving you with meters, for example, or kilograms, centimeters divided by kilograms, giving you centimeters. So yeah, as long as you're consistent with the units you put in, the units you get out should just be whatever length units you put in. Okay, so I want to calculate the total length of this thing first off, so that I can figure out the mass of each piece. I want to calculate the total length of this thing so I can get the mass of each piece. So, or at least what fraction of the total mass each piece would be. So I've got 3 plus 2.5. Oh boy, I really did make this awful for myself. 3 plus 2.5 plus 2 plus 3 plus 4 plus 1.5. At least I chose easy numbers. Plus, I didn't give a length for this, did I? Let's call that 1. Let's call that 1. So plus 1 plus 1.5 plus a final 3. Okay, and our total is, I'm going to do the 0.5s first. So 2.5 and 1.5, that's 4. And 1.5, that's 5.5. And then 5.5 plus the 3 and 2 is a 5, so that's 10.5. 17.5, 18.5, 21.5. Okay, so I'm just going to do one of the two coordinates. Let's do x. Let's say I want to find the x coordinate of the center of mass. You can find the y coordinate on your own. I'm just going to do one of them to save time. So how would we go about doing this? So I will say that the total mass of this piece of wire is m. So we'll say total mass is big M. And what I'm going to do is I'm going to take whatever length a particular piece is. I'm just going to cut this into straight pieces. So I'm going to make a cut here and a cut here. And basically at every corner, I'm going to make a cut and just treat it as a separate piece. And what I'm going to do is, since the mass is uniformly distributed, whatever fraction of the length that piece is, that's the fraction of the mass it is. So a piece that's 1/10 of the total length would have 1/10 of the total mass. That's what it means to have uniform density. That's what it means for the mass to be distributed uniformly. So for this first piece, it's going to be 3 over 21.5 m. I'll just say 3 and keep the 1 over 21.5 factored out at the end. So times 1 over 21.5. Actually, I don't think I left enough space here. I might have to actually move this aside. But 3 times its x-coordinate, well, its x-coordinate is 0. All the mass of this first segment is at x equals 0. Okay, what about this next piece? So this next piece is a horizontal piece, but we know if it's a piece of uniform density that its center of mass is right in the middle. So I can treat it as if all of its mass, I can treat this piece as if all of it is right over here. Come to think of it, I can do it for all of these pieces. I can just replace them with their midpoints and treat them as if the mass is over there. Okay, so this is going to be at half of 2.5, which is 1.25, and its mass is going to be, well, it's 2.5 over 21.5. Okay, times x is 1.25. Yeah, I'm definitely not leaving enough space for this. Okay, next is this piece over here, which has a length of 2, so that's going to be plus 2 times its x-coordinate is just going to be 2.5. Oh boy. What am I going to do about this? Let's just scratch this out and extend this line. I know it looks ugly, but the alternative is having to rewrite a bunch of stuff. So plus 2 times 2.5, and then next piece has a length of 3, and we're going to multiply it with, let's see, 2.5 plus halfway along this length, so half of 3 is 1.5, so that would be at x-coordinate 4. Okay, next up we have this piece which had a length of 4, so it'll be 4 over 21.5 of the mass times its x-coordinate is going to be at 2.5 plus 3. It's going to be at x equals 5.5. Next piece has a length of 1.5, so its mass will be 1.5 over 21.5 m. And then its x-coordinate is 5.5 plus 0.75, so that's 6.25. Okay, next piece is going to have a length of 1, so it's going to be 1 m over 21.5 multiplied by its x-coordinate 2.5 plus 1.5 plus 3, so that's 4 plus 3, that's 7. And then, which piece do I have next? Wait a minute. Yeah, okay, got it. I'm up here. So 2 more pieces left to go. Next piece is going to be 1.5 in length, so it's going to have a mass of 1.5 m over 21.5, and its position is going to be 7 plus half of 1.5, so that's 7.75. And lastly, we've got this thing with a length of 3, so a mass of 3 m over 21.5 divided, or not divided, times its coordinate is going to be, let's see, 3 and 3 is 6, and 2.5, that's 8.5. Oh my goodness. I probably shouldn't have made it that long, but now we're done with that. Put all of that in brackets times m over 21.5, and then divide by the total mass. So the m cancels out. The m cancels out. And let's see what we get. Oh boy. We've got 0 plus 2.5 times 1.25 plus 2 times 2.5 plus, that'll be 12, plus 4 times 5.5 plus 1.5 times 6.25 plus 7 plus 1.5 times 7.75 plus 3 times 8.5. All of that divided by 21.5 gets me position 4.526 approximately. So that's going to be 4.526. If that's 2.5 and that's 3, 4.5 would be, well, 4 is there. So 4.5 is around there. So somewhere a little past here, maybe somewhere like here, would be the x-coordinate of the center of mass. I don't even know how I would estimate whether or not this is correct, because keeping track of where all the mass is, well, let's see. So we've got 3 plus 2.5 plus 2. 3 plus 2.5 plus 2. So that's about 7.5, excluding this piece for now. About 7.5 there. And then I've got 4 plus 1.5. 4 plus 1.5 plus another 1.5. That's 7 already. That's 10. that's 11. Okay, so we've got a mass of 11 out of 21.5 over here, plus a little bit. And over here we've got 3, yeah, actually let me also add the 3 in here. So 3 plus 2.5 plus 2 is 7.5 plus 3, that would be 10.5. Okay, I must be calculating something wrong because there should be an equal amount of mass to the left as there is to the right. There should be just as much mass to the left of this line as there is to the right of it. And if I'm counting the whole 3, then I would actually have to have more on the left than I do on the right. So something is slightly off, but I'm not sure what it is, and I don't think we have the time to comb through this and double check and figure out what exactly is wrong. But at the very least, I hope from this you got the idea of how to work with this. So I'll give one last quick example, which is a plank of wood. This is actually a problem from one of my books. It gives you this plank of wood, except instead of, it was originally a full rectangle. It was originally just a full rectangular piece of wood, but then a quarter of it got cut off. And I'm not drawing it really well here, but it should be a quarter. And they ask you to find the center of mass of this remaining chunk. So what you would do here is kind of similar to what I did here. You would just divide it into these equal pieces, and then you would just use the centers of mass of each of those pieces and just replace those pieces with those point masses and treat it like our original problem over here. And you would just give each of them a mass of m. And then whatever the coordinates are, let's say it's, I don't know, 2, maybe not 2. Let's make this, let's say that this is 4 centimeters over here. And let's say that this is 10 centimeters, for example. So each chunk would be 5 centimeters wide and 2 centimeters high. And yeah, for this one, you would just give its coordinate as half of 5, so 2.5 comma 1. And that one would be at 2.5 comma 3. And that one would be at 7.5 comma 1. And you would just do what we normally do. Take each mass. If the object doesn't have a known mass, just call each one. You could call the total mass big M and give each of these a mass of 1/3 m, or you don't even have to do fractions. You can just give each of them an equal mass and call that big M and say that the total mass is 3m. So you would just you just have to remember to put 3m in the denominator instead. Basically, that would be the same as factoring out the 1/3. So either a 1/3 m for all the numbers that you put in the numerator, or you move that 1/3, you move the 3 from it down and just get a 3m in the denominator. Either way, you would get the same result. Another option, if you're feeling brave, is you could try and take the original block. You could take the original block before anything was chipped away from it. You could take the original block and assign it a mass of big M and use its center of mass plus a block of mass negative 1/4 m and use its center of mass and subtract that in the numerator and then divide by the total mass, which would be all of big M plus the negative 1/4, and do it that way and see if you can get the same result. So I think that is what I will leave as a challenge for you. But yeah, for everything else, you'll have to wait until we get to the calculus part of the course. For everything else, we'll be looking at either odd shapes that require calculus even when the mass is uniform, which actually I can't think of anything like that off the top of my head, but maybe that's because I'm tired right now. And the other thing will be, of course, non-uniform mass distributions. We will look at a lot of the, well, I don't want to say a lot, but we'll look at some of those cases and learn how to deal with them using calculus techniques once we get to that part of the course. We're getting there. One last thing, which is center of gravity. So center of gravity is actually not too hard to calculate. It's basically the same formula as center of mass, except instead of each mass multiplied by its position, it's going to be each mass times g multiplied by its position. So if I wanted the center of gravity for this over here, for example, I would do 0 times 3 times g plus 0 times 2 times g plus 4 times 5 times g divided by 3g plus 2g plus 5g. Wait a minute. So I just multiplied everything by g's in the top and in the bottom. Don't the g's just cancel out? Yes, the g's cancel out. That's why the center of mass and center of gravity are usually the same position. Except if you're dealing with an object that is big enough, we're talking tens of thousands of meters at the very least, then some parts of it, what you would actually do is you would do y1 times m1 times g1 plus y2 times m2 times g2 plus y3 times m3 times g3, and so on. You would have different g's at different heights. Once the altitude of your object, if you're talking about, I don't know, some ridiculously tall skyscraper, once you reach high enough altitudes, once you have an object that's big enough and reaches a high enough altitude for detectable changes in the acceleration due to gravity, that is when center of gravity starts becoming different from center of mass. So as a very, very exaggerated example, let's suppose you have some ridiculous tower. Or better yet, let's say you have a space elevator. Let's say we somehow get over all of our idiotic tendencies as humans and actually collaborate and build a space elevator one day that just allows us to send things, transport things into outer space without having to burn a ridiculous amount of rocket fuel. Imagine what would happen if that elevator ever malfunctioned. Oh boy, would I hate having to be the guy that has to fix that. But anyway, so your space elevator, its center of mass, assuming that it's just made symmetrically, would be right in the middle, but where would its center of gravity be? Well, its bottom side is going to have a larger g, right? It's going to have a larger acceleration due to gravity on the bottom than the top. So the center of gravity is actually going to be biased towards the bottom. The center of gravity, so here's center of mass, center of gravity will be somewhere closer to the bottom. Since the bottom experiences a stronger gravitational force than the top, your center of gravity will be somewhere down here. And the taller the tower, the bigger this gap between the center of mass and center of gravity will be. Tower, space elevator, whatever I called it in the beginning. So there you go. That is the difference between center of mass and center of gravity. It's not going to matter for like 99.9% of the scenarios that they're going to throw at you. I would say 100%, but you never know. They might throw a curveball at you. But there it is. Just understand conceptually what the difference is. But center of gravity and center of mass, for the problems that you'll be seeing on the AP exam, I can practically guarantee that you'll always be able to get away with treating them as being the same. And I think that's it. Wait, no. One more thing. One more thing, and I will leave this as homework. Find if I have two objects that collide, in such a way that their momentum is conserved, find the velocity of the center of mass before and after collision. Find v center of mass before versus after collision. Is that all visible on the screen? Yes. V center of mass before versus after collision for a pair of blocks, and let's say that block 1 has mass m1 and is initially moving at velocity v1 initial, and block 2 has mass m2 moving at velocity v2 initial, and of course after collision their velocities become v1 final and v2 final. So very, very generic. We don't have any known values. See what you can come up with if you try to find the velocity of the center of mass before versus after their collision. See if you can spot anything interesting that happens there. And assume, of course, that momentum is conserved because you kind of need that here. And let me think, was there anything else I needed to give you for this? So, if you know how to calculate the position of the center of mass, then all you have to do is take your position of center of mass. I guess you would only need x in this case. Usually we only deal with one-dimensional horizontal collisions after all. Then what you can do is you can just divide by time, or if you know your calculus, differentiate with respect to time to get your velocity of the center of mass. If you have position of the center of mass as a function of time, if you can write position of the center of mass as a function of time, then you can use that to get your velocity of the center of mass. And I think that is the last thing I have to say. I'm tuckered out. I need to get going. Hopefully I'll be able to stream again tomorrow, but if things don't work out, if I'm needed elsewhere, then we'll just find another time for it. But the topic for next time, and I probably should have said this for the Physics 1 students. Actually, wait, I've been saying it throughout. the topic for next time, we're going to dig deeper into moment of inertia and also look at some other new equations that will open up for us. Things like rotational kinetic energy and whatnot will probably be brought up, but I imagine my initial focus will be on just moment of inertia calculations. And yeah, that is all. Class dismissed. I'll see you next time.